University of California, Santa Cruz, towards live programming environments for statically verified JavaScript, a dissertation submitted in partial satisfaction of the requirements for the degree of Doctor of Philosophy in Computer Science by Christopher Schuster, December 2018. This dissertation of Christopher Schuster is approved by Professor Cormac Flanagan, Chair, Professor Charlie McDowell, Professor Robert Hirschfeld, Gilda Braca, PhD, Lori Kletzer, Vice Provost and Dean of Graduate Studies. Abstract. Towards live programming environments for statically verified JavaScript by Christopher Schuster. This dissertation includes contributions to both live programming and program verification and explores how programming environments can be designed to leverage benefits of both concepts in an integrated way. Programming environments assist users in both writing program code and understanding program behavior. A fast feedback loop can significantly improve this process. In particular, live programming provides continuous feedback for live code updates of running programs. This idea can also be applied to program verification. In general, verifiers statically check programs based on source code annotations such as invariants, pre, and post conditions. However, verification errors are often hard to understand, so programming environment integration is crucial for supporting the development process. The research for this dissertation involved the implementation of EsVerify, a program verifier for JavaScript, as well as prototype implementations of multiple programming environments. These implementations demonstrate potential benefits and limitations of proposed solutions and enable empirical evaluation with case and user studies. Additionally, the proposed designs were formally verified in order to explain the core idea in a concise way and to prove properties independent of concrete specifics of existing systems and programming languages. The resulting systems represent possible solutions in a vast design space with various contributions. The research on live programming showed that a programming model that separates event handling from output rendering enables not only live code updates, but also runtime version control and programming by example. For program verification, EsVerify represents a novel approach for static verification of both higher order functional programs and dynamically typed programming idioms. EsVerify can verify non-trivial algorithms such as merge sort, and a formal proof in the lean theorem prover shows that its verification rules are sound. Finally, a programming environment based on EsVerify supports inspection and live edits of verification conditions, including step-by-step debugging of automatically generated tests that serve as executable counterexamples. As part of a user study, participants used these features effectively to solve programming tasks and generally found them to be helpful or potentially helpful. Acknowledgements. I owe my deepest gratitude to my advisor, Cormac Flanagan, for his ongoing support, guidance, and for always being available for discussions. I am proud to be one of his students. I am also very thankful to my mentor, Charlie McDowell, and his helpful advice not only for my research, but also for teaching. And I want to thank Robert Hirschfeld and Gilda Bracha for serving on my committee and providing useful feedback. Additionally, I want to thank my lab mates at the Software and Languages Research Group at UCSC. I will fondly remember our discussions about programming languages, technology, games, politics, and metaphysical topics. In particular, Thomas Schmitz answered many of my questions about theorem proving. Dustin Rhodes often surprised me with his pragmatic and unconventional perspective. Soham Banerjee never shied away from debates on any topic. And Tim Disney is one of the reasons why JavaScript became the basis for this dissertation. Furthermore, I also want to thank important colleagues and mentors that supported me during internships, especially Marcelo Sierro, Dan Ingalls, and Robert Cron. During my years in Santa Cruz, I consider myself lucky to enjoy the friendship of Josh Pang, Cyan Park, and many others on this long journey. Lastly, this thesis would not have been possible without the support and understanding of my family. Nobody actually creates perfect code the first time around, except me. But there's only one of me. Linus Torvalds. Chapter 1, Introduction. A computer is a universal machine in the sense that anything that can be computed at all can theoretically be implemented and executed by any Turing-complete system. The sequence of steps taken by the computer are expressed by program code, written in a programming language. Different programming languages may have different formal and mental models and abstractions, but ultimately have the same power for expressing computation. Due to being universal, there are infinite possible programs a computer can execute. Therefore, selecting precisely the desired program behavior requires a very precise language. In that sense, programming languages fundamentally differ from natural languages which rely on context, assumptions, and cultural knowledge. This difference causes programming to be extremely difficult. In particular, it is often relatively easy to informally describe ideas about expected program behavior, but tedious, frustrating, and error-prone to implement this behavior in a programming language. In the end, most regular computer users do not program their computers and instead treat software as incomprehensible, opaque products that cannot be customized to expectations. Even for professional software developers, programming has generally not become easier or more intuitive over the last decades. To manage complexity, professional software development requires knowledge about a continuously evolving plethora of different tools, language features, and abstractions. In contrast, the way programmers interact with their programming environment has changed relatively little over time, and therefore offers a high potential for improvement. As a general model for thinking about tool interaction, Norman proposes the gulfs of execution and evaluation. In that model, the tool user has intended goals that are executed with actions and evaluated based on feedback. A tool is easier to use if execution and feedback are more closely connected to the intended goals. Taking a water faucet as an example, the goal might be a certain temperature and pressure, but if two provided handles control the flow of warm and cold water directly, the user needs to develop a mental model of the mixing process through trial and error in order to achieve the result. An alternative tool design with a handle for temperature and a separate handle for pressure would make it easier for the user to achieve the desired goal. Figure 1.1 shows this model applied to programming environments. Here, the programmer needs to understand the current behavior of a program and how it can be changed through code edits to match the expected behavior. The design of the programming environment should take this iterative process of execution and evaluation into account to simplify the programming process. It is noteworthy that this inherent tool problem persists independent of progress in machine learning and artificial intelligence because the intended behavior still needs to be communicated and validated in a way that also the user to understand and iteratively change the program behavior. Programming environments can support the iterative process of execution and evaluation by reducing the time gap between code edits and feedback. In particular, live programming aims to provide immediate and continuous feedback for code edits to running programs, in addition to manual evaluation of the program behavior and whether it conforms with the goals and the mental model of the programmer. It is also possible to automatically check whether the program code is consistent with a second formalized description of the intended behavior. For example, by providing examples in the form of executable tests, any discrepancy between expected test outcome and program code can be detected. Besides tests, the code can also be checked against annotations such as types, assertions, and invariants. If these annotations are expressive enough to describe functional properties, this enables an automatic static program verification. This dissertation includes contributions to both live programming and program verification and explores how future programming environments can be designed to leverage benefits of both live programming and program verification in an integrated way. 1.1 Live programming. For any non-trivial application, it is unlikely that the intended behavior can be implemented correctly without any feedback or experimentation. Rather, programming is an iterative process involving trial and error. Programming environments can support this process by providing detailed feedback about the program execution, e.g., allowing the programmer to observe the state of variables and sequence of steps with a debugger, and by providing immediate or even continuous feedback for code edits, e.g., allowing the programmer to edit the code and observe effects without having to recompile and restart the program. These objectives are not only important for the concrete design of the programming environment, the latter also affects the design and semantics of the programming language. The ability to change the code of a running application would radically change the common edit, compile, restart cycle and enable quick experimentation and exploration. As an analogy, it is significantly simpler to continuously adjust a water hose to hit a target than to aim and shoot with a bow and arrow. As Figure 1.1 illustrates, interactions with programming environments involve an iterative cycle of code edits by the programmer and feedback to evaluate how these edits affect the program behavior. Live programming is particularly promising for improving this process and supporting human understanding due to its emphasis on continuous feedback and learning by doing. The positive effects of practical experience and experimentation on the learning process have been shown empirically and form a core principle of computer science education. The manual effort involved in getting feedback to change a code, change in the code, and the time delay it takes for these changes to become visible discourage quick experiments in this kind of trial and error setting. Essentially, the programmer should not be required to mentally simulate mundane parts of the program if the environment can do it well. Therefore, live programming aims to provide immediate and continuous feedback without the need to switch back and forth between editing the code and running the program. An unavoidable challenge of live programming is the inherent entanglement between execution state and program code. Code updates in the presence of these dependencies may require the programmer to specify data conversions, which delay feedback and thereby hinders live programming. Possible solutions are often trade-offs that restrict potential update points in the execution or compromise on consistency by leaving references to outdated code and then new execution state. 1.2 Program verification. For large and complex projects, any specification of the intended behavior is prone to have errors, i.e. unintended differences with the expected behavior of the program. The executable program code itself is the most complete specification of the behavior, so bugs in the code often cause the program to stop working or misbehave. However, if the intended behavior is described with multiple different specifications, the programming environment can automatically check whether these specifications are consistent with each other and thereby reduce the risk of errors going unnoticed. Besides the actual program code, automatic tests, type annotations, and assertions are often used to specify expected behavior. Since tests are executable programs, any discrepancy between the program code and the test assertions can be detected simply by running the tests. Therefore, failed tests can be examined with the same debugging tools that enable stepping through the code and inspecting the execution state. This integration enables programmers to obtain detailed and concrete feedback and greatly contributed to the adoption of automatic testing as a general practice in software development. However, tests require concrete example inputs for their execution. Therefore, automatic testing can only check the program behavior for a finite set of possible inputs. This is also true for random testing approaches, such as quick check. Depending on the test coverage and the expectations about robustness, this limitation may be more or less severe. For example, programs that receive input from untrusted sources may need to guarantee certain security properties in the presence of adversarial inputs, while programs for visualizing data sets might be checked adequately with a few manual tests. Figure 1.1a shows an example of a max function with an accompanying unit test. Here, the expected return value can be checked against a concrete result. Alternatively, it is also possible to merely check whether the result is at least as big as the input arguments. In addition to tests, types are a way to constrain the possible program behavior such that variables, function arguments, and function results can only be certain sets of values. Simple types are often too imprecise to specify the functional correctness of a program, but the type systems can still be used to ensure the absence of certain categories of errors. For example, memory safety in the absence of segmentation faults can be ensured by dynamic type checking, as in JavaScript and Python, or by a combination of dynamic and static type checking, e.g. Java and C#. With explicit type annotation in the code, the programming environment can also provide feedback about discrepancies between the stated type and the runtime values. Especially static type checking can be useful as it provides guarantees for all possible executions, but even if static type checking fails,
gradual typing, and dynamically enforced contracts can be used to obtain helpful feedback for understanding and fixing potential bugs occurring at runtime. The main drawback of type checking is the trade-off between expressiveness and overhead for the programmer. Primitive type systems often have a simple type syntax, support subtyping and automatic type inference, and provide helpful error messages, but are incapable of expressing functional correctness properties. Rich type systems with dependent function types, type refinements, and effects are expressive enough to more precisely specify the intended program behavior, but often require explicit annotations and a mental model of the intricate type checking algorithm in order to comprehend the error messages and the limitations of type inference and subtyping. Figure 1.1b shows an example of a max function with annotations. While the annotation in lines 2 and 3 use basic types as common in TypeScript, the comment in the first line specifies a more precise return type that establishes a minimum bound for the result with a refined type. As a third alternative, the intended program behavior can also be described with assertions, i.e., logical propositions about values and variables in the code. Checking of assertions is closely related to type checking. However, while type checking is based on a separate syntactic class of types and typing rules that compare, infer, and manipulate these types, assertion checking is about determining the truth of a proposition in logic. Depending on the assertion language, different methods can be used to check assertions statically or dynamically. If assertions are simple Boolean expressions, they can be checked at runtime by simply evaluating these expressions as part of the execution of the main program. However, assertions involving higher order functions cannot be checked immediately for all possible values, so dynamic checking of function arguments and results has to be deferred until these values are available. Similarly to contracts, static checking of assertions, i.e., program verification, is comparable with rich and expressive type systems, as it enables the programmer to express functional correctness properties and check whether the program code conforms to these properties, but it also has similar disadvantages in terms of overhead and complexity. In particular, the program verifier requires annotations such as pre-post conditions and invariants in order to prove that an assertion is valid for all values, and the programmer has to know the basic verification process in order to understand and fix verification issues. Figure 1.1c shows an example of a max function with annotated pre and post condition. By assuming the preconditions, a program verifier, such as verify, can prove that the post condition holds for all possible values of A and B. 1.3 Research Goal and Method. Both live programming and program verification are well-known concepts that have been studied and applied for decades. The idea of live programming can be traced back to systems with self-contained development tools such as Smalltalk, but there is also renewed interest with software projects such as Swift, Playground, and Elm, as well as academic research conference such as the Live Workshop. Similarly, program verification and formal methods in general have been the topic of extensive prior research, with impressive achievements in the last years, such as a verified C compiler and a verified microkernel. Even for non-academic projects, verified programming languages such as Daphne are increasingly adopted to verify correctness properties of commercial software. However, the integration of program verification into development environments is a relatively new topic, with many open questions. The complexity of the verification process and the resulting usability issues for the programmer are still major obstacles for program verification. While live programming is generally orthogonal to static checking, the live programming perspective seems to provide an ideal approach for exploring novel solutions with fast feedback cycles. The central question of this dissertation research is therefore, how can live programming environments support verification to provide a better programming experience. There is a vast design space of possible solutions to this question. A comprehensive evaluation of a possible solution would require a stable and mature implementation of both a program verifier and a live programming environment. Unfortunately, these tools require immense engineering effort to create. For example, the projects mentioned above generally have teams of full-time developers or active open source communities. In order to explore and evaluate possible solutions as part of this dissertation research, I followed an approach that instead relies on prototype implementations and simplified formal models. The prototype implementations created as part of this dissertation are not ready for productive use on real-world projects. However, they allow experimentation with smaller code examples, and by using JavaScript as both source and object language, they enable live online demos that can be used in a browser without local installation. These demos illustrate with practical examples the potential benefits and limitations of solutions to a wider audience. Furthermore, formal definitions summarize the core ideas of the proposed solutions in a concise way. By omitting orthogonal concepts of actual programming languages, the formalism clarifies how the approach can be applied to a wide range of languages. In addition to sketching potential solutions with prototype implementations and formal definitions, the proposed design also has to be evaluated in order to determine its properties and to compare it with other solutions. Here, prototypes can be used for limited case studies such as implementations of well-known algorithms, as well as user studies with participants who solve smaller programming tasks with the tool and provide feedback about their experience. Additionally, a formal definition also enables formal proofs of properties such as soundness. 1.4 Outline and Contributions. Chapter 2 presents an approach for live programming in the context of graphical user interfaces and describes how this approach enables back-in-time debugging and programming by example. As explained in section 1.1, live code updates may cause issues due to references and dependencies between execution state and code. While these dependencies cannot be avoided completely, a programming environment can provide a better support of live programming by restricting the programming model such that event handling is separated from output rendering. This approach allows live code updates in between events and back-in-time debugging while re-rendering the output at each step to provide immediate and up-to-date feedback. Additionally, this approach also enables a form of programming by example such that code edits are automatically inferred from output examples or direct manipulation of the user interface. In addition, a concrete prototype implementation The chapter also presents a cursory formalization of these concepts. Chapter 3 introduces sVerify, a program verifier for JavaScript based on SMT solving. sVerify is able to verify both higher-order functions and dynamically typed programming idioms in JavaScript and is designed with the goal of ensuring quick feedback and comprehensible verification process. In particular, sVerify explicitly avoids automatic inference procedures and heuristics that are common in other program verifiers. For example, it uses a custom trigger-based quantification instantiation algorithm that is more robust, predictable, and simpler than default instantiation heuristics in SMT solvers. As a result, sVerify requires more explicit annotations to verify some programs, but verification errors are easier to understand and inspect with a programming environment. Chapter 4 includes a formal development of program verification that follows the sVerify approach. The formalism defines program verification for Lambda S, a pure functional core language. The verification rules involve verification conditions, VCs. Quantifiers in these VCs are instantiated according to a custom quantifier instantiation algorithm, and validity of the resulting propositions is based on an axiomatization of the SMT solver. Based on this formalism, it can be shown that verification is decidable, i.e. verification terminates for all input programs, and sound, i.e. verified programs adhere to their specification during evaluation without getting stuck. Chapter 5 describes how verification errors in sVerify can be turned into executable tests that serve as concrete witnesses. Error messages based on the VC itself are often not detailed enough to explain verification errors to the programmer. However, by generating an executable counterexample based on the output of the SMT solver, the verification error can be inspected in terms of concrete variable values, and its execution can be debugged step by step. The test generation, therefore, represents a basis for further integration into a programming environment. Additionally, some verification errors are caused by limitations of their verifier and insufficient annotations rather than bugs in the code. Automatically generated tests can assist the programmer in distinguishing these errors and fixing annotations. Chapter 6 prevents IDVE, a prototype of a programming environment that integrates program verification with interactive tool support. In particular, IDVE shows counterexamples with concrete values directly in the code editor, and it features a verification inspector. The verification inspector displays detailed information about the VC, such as assertions and assumptions, and it also enables step-by-step debugging of the automatically generated test. Furthermore, the verification inspector also enables the programmer to edit assertions and assumptions of a VC in order to support quick feedback and experimentation similar to live programming. Thereby, the verification inspector allows programmers to explore the verifier state without manually adding assert statements to the code, analogous to how interactive debuggers let programmers avoid printf debugging. Additionally, this chapter also describes an evaluation of IDVE with an online user study with 18 participants, where participants solved small programming and verification tasks and answered a survey about their experience. Finally, Chapter 7 surveys related work, and Chapter 8 concludes this thesis. Appended to this thesis is the lean source code of the formal development and the provided theorems in Appendix A. Additionally, Appendix B lists the programming tasks that were part of the user study, and Appendix B includes a record of all survey answers by participants in the user study. To summarize, this dissertation research includes the following contributions: a live programming environment for event-based GUI applications based on a programming model that separates event handling from output rendering, an integration of live programming with programming by example based on direct manipulation of the string literals in the user interface, an approach for verifying dynamically typed JavaScript programs with higher order functions, a bounded quantifier instantiation algorithm that enables trigger-based instantiations without heuristics or matching loops, a prototype implementation called sVerify, a formalization of the verification rules, and a proof of soundness in the lean theorem prover, an extension for sVerify that automatically generates test cases for failed verification conditions with synthesis of function values and assertion violating calls, an integrated development and verification environment, IDVE, with a novel interactive verification inspector and debugging interface, and a user study to evaluate whether and how the IDVE assists with simple programming and verification tasks. If there is any delay in that feedback loop between thinking of something and building on it, then there is this whole world of ideas which will never be. Brett Victor. Chapter 2, Live Programming Environments for JavaScript. This chapter characterizes live programming as a feature of programming environments, distinguishes it from other related concepts, outlines challenges, and describes a live programming approach for GUI applications. This approach restricts the programming model such that event handling is separated from output rendering and thereby enables live code changes between events while continuously updating the rendered output. Besides a concrete implementation of a live programming environment for JavaScript and a language-independent formal definition, this chapter also presents live programming by example as an extension to live programming that infers code updates from output examples and by direct manipulation. 2.1 Introduction. The term live programming is used in different contexts with no clear consensus on its definition. Live programming can denote the act of programming as part of a live art or music performance in front of an audience. Another use of the term live programming involves a programming environment that executes parts of a program while displaying intermediate results alongside the code, similar to interactive workspaces / notebooks or playgrounds. However, this research focuses on live programming as the ability to change the code of a running application without restarting it, also known as hot swapping, and provides immediate feedback about these code changes. Live programming is closely related to dynamic software updating, DSU, but focuses on development tool support rather than patching of production systems. Ambiguities and limitations of live code updates are not catastrophic failures for live programming environments. Instead, live programming favors a best effort approach that minimizes the overhead for the development process. In contrast, DSU requires programmers to precisely specify data migrations in order to resolve ambiguities and ensure persistency of production data. Furthermore, live programming goes beyond self-contained development environments with live code updates such as Smalltalk and Lisp. In live programming environments, immediate and continuous feedback about code updates is not a side effect, but a primary goal. In particular, this often involves re-execution of the changed code as well as dependent parts of the program to see the effects of the code update. For more comprehensive discussion and survey or existing work on live coding, live programming, and exploratory programming, see Rhine et al. Using an arbitrary programming language with function values and heap references as an example, Figure 2.1 shows the entanglement between source code and execution state. Live programming involves runtime updates to the code while retain parts of the execution state. So each of these dependencies poses a question. At which point does the execution, i.e. the program counter, resume if the currently executed statement or expression is changed? What happens to the current function call stack if the corresponding functions are removed from the code? How are closures maintained if the surrounding code is modified? Can the currently visible output be updated to reflect the new version of the rendering code? What happens if the format and shape of heap allocated objects is changed in the source code? A programming system with support for live programming has to answer these questions and addresses potential inconsistencies. This often involves trade-offs such as restricting live programming to certain fragments of the source code, eliminating potential updates in the execution, or leaving references to outdated code in the new execution state. 2.2, separating rendering from event handling. It has been shown that certain application architectures enable live programming for a large range of program edits without manual data migration. A live programming system with continuously updated feedback was first presented by Hancock and further explored by systems like Superglue, which uses dynamic inheritance and explicit FRP signals. Burkhardt et al. And McDermott presented a solution to these challenges for reactive event-based systems, in contrast to DSU systems, which guarantee safe updates with the cost of manual data conversions. A best effort approach better suits the goals of live programming. To prevent outdated code in closures and avoid complicated transformations of these closures. The global application state is restricted to not contain any function values. Furthermore, if the code for rendering output is separated from event handling code, it can be evaluated to continuously to keep the displayed output up to date. More recent work outlined the possible design space between live programming systems that resume computation with a possibly inconsistent state and systems that record and replay execution, as well as introducing managed time as a concept for supporting both live programming and time travel. This section exemplifies the obstacles for live programming, introduces a particular architecture pattern for stateful reactive GUI applications that support continuous feedback in a live programming environment, and briefly discusses ways to enforce this programming model statically and dynamically. 2.2.1 Traditional/imperative GUI programming. To illustrate the approach, it is useful to first consider a traditional programming style for GUI applications. Listing 2.1 shows a jQuery implementation of a graphical click counter. As a minimal example of an interactive application, the user interface consists of a text span to display the current value of the counter, as well as a button. Here, the jQuery function $, is used to select elements in the browser document object model DOM based on their ID attribute, attach event handlers, and manipulate the DOM. The JavaScript code uses a global variable count and registers an event handler for the button such that every click increments the counter and updates the display. Independent of coding style, this imperative way of changing the user interface and registering event handlers poses a significant obstacle for live programming. As an example, renaming count to clicks involves code changes to lines 1 and 7. In a live programming environment, these changes should ideally update the registered event handlers, which are closures stored in the DOM state, and update the visible output of the program without modifying the application state, i.e. the variable count should remain unchanged. However, this essentially involves removing the obsolete event handlers from the DOM, registering the new event handlers, reevaluating line 5, and updating the output without mutating the state. Do. 2. The structure of the code. The only choice is to update the event handlers without reevaluating them, thereby displaying an inconsistent output until the next click event, or to restart the whole application, thereby losing the current value of count and losing the benefits of live programming. 2.2.2 Model View Update Pattern. In order to solve the problems outlined above, a program can be separated into 3 parts: a model, a view, and an update component. This architecture is similar to the well-known and popular Model View Controller MVC pattern. Since its origin in the context of Smalltalk, MVC has been adapted and applied in different ways for building user interfaces for both desktop and web applications. Following the usual object-oriented design methodology, the model, the view, and the controller in the MVC are sets of objects that fulfill different roles of the application and adhere to the principle of separation of concerns. The model is responsible for domain, logic, and state. The view is the visible user interface, and the controller reacts to user input by changing the model, the current view, and its own state. It is noteworthy that model, view, and controller all have internal state, which has to be kept consistent with imperative updates due to the lack of declarative dependency definitions. The model view update pattern, MVU, is an adaptation of MVC that incorporates ideas from functional and reactive programming in order to provide a more declarative programming style. In contrast to MVC, the update component only operates on the model and cannot directly access the view, while the view only generates a user interface without maintaining internal state. Therefore, both the view and the update components are stateless and can be understood as pure functions. Essentially, the model encapsulated the entire application state, including the state of the UI. The view returns the output/user interface based on the current model, and the update component processes events, yielding a new model. It is noteworthy that the separation of model, view, and update also applies to reuse of code as part of a library or larger application, while component-based UI systems use a single component, object, or class as composable and reusable abstraction. MVU requires the model, view, and update to be composed separately. There are variations of MVU and other patterns for UI architectures that advocate unidirectional data flow, which have recently become popular for developing web applications such as Redux, /web, and the Elm architecture, and reactive programming in general. However, the approach in this chapter focuses on the MVU pattern outlined above due to its simplicity relative to more sophisticated solutions. Listing 2.2 illustrates how the example in Listing 2.1 can be rewritten with the MVU pattern. Here, the model simply consists of a global variable containing the current click count as integer. In more complex applications, the model would be defined in terms of user-defined classes and data types. Updates to the model are initiated by event handlers that are declaratively bound to elements of the UI. In this case, the inc function is bound to the button in line 14 and simply mutates the model by incrementing the count. Finally, the view is a top-level render function that may invoke other view functions and return a tree structure as the output. The details of how this tree structure is defined and constructed is application-specific and insignificant for live programming. In Listing 2.2, inline XML, HTML tags are used to create a user interface, also known as JSX syntax, popularized by React. 2.2.3 User interactions in MVU applications. Conceptually, the MVU architecture style handles user interface interactions as input event. The output is generated by the view based on the current state of the model. Any interaction by the user, such as clicking with a mouse or pressing a button on the keyboard, represents an input event. This event, alongside the previous state of the application, initiates an event handling procedure that results in a new and potentially changed model. The view then renders the new model by generating a new user interface. It is important to note that this re-rendering is initiated and managed by the environment or framework and not invoked by user code. This avoids redundant rendering of unchanged parts of the output and enables different DOM updates. 2.3 Live Programming Environment Integration. The MVU architecture pattern described in the previous section has advantages for live programming environments. In particular, it enables continuous feedback for live code updates and back-in-time debugging and runtime version control. 2.3.1 Code updates. As illustrated by Figure 2.1 in Section 2.1, any approach for live programming needs to resolve the inherent entanglement between code and execution state, including the current program counter, the function call stack, and closures. An event-based model of program execution and an MVU architecture style, with additional restrictions, avoids some of these links and thereby facilitates live programming. First, the execution is assumed to be strictly single-threaded with a single main event loop, as common in JavaScript. In this model, the program code is not actively executed by any thread while the system is waiting for the next event. Therefore, the execution state between events does not contain a current program counter or active call stack with regards to the application code. This greatly simplifies code updates at these update points. Second, the MVU architecture style summarizes the complete application state in the model. Therefore, the view and update components can be swapped at runtime while retaining most of the execution state. Finally, the application state is restricted to not contain or reference function values. In some cases, it might be feasible to swap an existing function value for a newer version of the same function. However, the original function was removed from the code. The function value might become outdated. Additionally, code updates might move or rename function definitions and thereby cause ambiguities if the identity of functions is determined solely based on the previous and updated version of the code. As a possible solution, the programming environment could model code updates as semantic actions instead of plain text edits to resolve these ambiguities. Furthermore, if a function value references variables in the surrounding scopes, then even changes to the surrounding code could affect values in the environment of the closure. Conceptually, these same issues also apply to objects as instances of class definitions. However, the identity of named classes is less prone to be confused, and methods are not usually closing over an environment. In conclusion, avoiding function values in the application state ensures that code updates do not result in ambiguity or outdated references, but alternative approaches might enable live updates even in the presence of closures. Figure 2.3 depicts how the code of the view and the update component in an MVU application can be updated at runtime. It is important to note that changes to the view code result in a re-rendered output. Thereby, the programmer is able to get immediate feedback about code changes. Changes to the update component, on the other hand, only take effect at the next event to be processed. As a potential alternative, it would be possible to replay past events with a new update component. 2.3.2 Navigating execution history and code versions. As described in the previous section, the MVU pattern allows the application state to be re-rendered on demand with a stateless view of function. In addition to the current application state, this also enables any previous state in the execution history to be displayed as a simple form of time travel, debugging back in time. On a high level, each step in the execution history is an event, and each event handling procedure produced a corresponding model. Therefore, it is possible to use the current view to visualize past states of the application as shown in figure 2.4a. The implementation of this trace could either maintain snapshots for the model and event log to be replayed, or a combination of both. Similarly, the concept of live code updates can be extended to runtime version control. Instead of swapping the view and update code based on a source edit, the programming environment loads a different version of the code while retaining most of the execution state. Runtime version control is a common technique in self-supporting systems. For example, Monticello enables programmers to load different versions of a package into a live squeak/Smalltalk environment. In the context of MVU applications, navigating the version history has the additional benefit of continuous updates to the output as depicted in figure 2.4b. 2.3.3 Enforcing Mvu Pattern. As mentioned in section 2.2.2, the view should not be able to alter the state of the model. In pure functional programming languages, this is trivially the case. In languages with imperative updates, such as JavaScript, the view may accidentally change the model when rendering the output. This may cause unintended effects with live code updates. For example, automatic re-rendering after a code change might corrupt the model state in an irreversible way. In that case, the programmer has to restart the application and loses the benefits of live programming. However, it is possible to dynamically and statically detect and enforce that the view does not alter the model. For example, a dynamic contract could check that the model before and after each rendering is identical, or alternatively, an immutability proxy membrane could grant read access but prohibit mutation. Instead of detecting mutation at runtime, it would also be possible to statically check the code with a type and effect system. This avoids the performance overhead of dynamic checking but might reject valid programs. While mostly preferable for languages with type annotations, static analysis methods can also check unannotated dynamically typed languages such as JavaScript. Similarly, it is possible to either statically or dynamically enforce that the model does not contain or reference function values / closures as discussed in section 2.3.1. 2.3.4, Formalism. The previous sections described a live programming approach for JavaScript. However, this approach can also be generalized and applied to other languages that have an event-based execution. This section gives a formal definition of a minimal language in order to clarify the minimal requirements for the program structure and execution, and to model live code updates as system interactions alongside regular event processing. Figure 2.5 formally defines the structure and transition relation for a generic live programming system based on the MVU pattern. The state of the system is summarized by the application state M model, rendering code V, view, and event handling code U, update, and system transition. MVU I goes to O. MVU is triggered by a system interaction I, which produces output O. In particular, the system processes both regular input events Q and runtime code updates while providing continuous feedback. In this formalism, the output of the application is not generatively imperatively, e.g. via printf statements. Instead, it is summarized as a single value O, e.g. the DOM of a JavaScript application or the frame buffer of an OpenGL application. MVU and the output O are assumed to be values in a language with lambda abstractions and function application, but the syntax definitions for values and expressions E depend on the concrete programming language implementation and are mostly left unspecified. Regular input events, such as mouse clicks, are processed according to e-event transition rule. The update function U is invoked with the current application state M, and the event data Q yielding a new model M prime. This model is then used by the view V to render the new output O. The system also supports live program, i.e. hot swapping of code at runtime with immediate feedback. The rule eSwap describes how new versions of the view V prime and the update U prime code are replacing the previous code V and U. The new view V prime is used with the current application state M to provide feedback O about code changes. Changes to the update code are not immediately visible, but subsequent events will be processed with U prime instead of U. 2.3.5 Implementation. The implementation of live programming approach as a web-based online programming environment for JavaScript involved both user interface design as well as techniques for checking conformance to the MVU programming model. Its source code and a live demo are both publicly available. The environment features a code editor with syntax highlighting and a side panel for navigating the execution and version history and displaying the output. More advanced features such as project management for programs with multiple files and nested folders are not currently available. A screenshot of the programming environment is shown in figure 2.6. The code editor 1 includes the complete source code of the application. Every change made in this editor creates a new version that is appended to the version history. A slider in the time control panel 2 allows the programmer to restore a previous version indexed by its revision number, and also to load and save the current file 3. Similarly, the programmer can go back in time to a previous application state with slider controls for each state corresponds to an input event in the application trace. The application is assumed to be continuously running, but execution can also be manually restarted 5. This is particularly important if changes made to the code are incompatible with the current state, or to ensure that changes to a global initializer takes effect. Finally, the third panel 6 enables the programmer to see the current output, examine its underlying HTML structure, and inspect the state of global variables. As discussed in section 2.3.1 and 2.3.2, editing the code or navigating the version and execution history causes the output to be refreshed in order to provide continuous feedback. In addition to the user interface of the programming environment, the implementation also involved management of the MVU programming model that enable event processing and live code updates. In particular, the programming environment wraps event handlers such as the inc function in figure 2.6 in a function that automatically schedules a re-rendering of the output after each event. Furthermore, the programming environment also ensures that there is a global render function returning the output as a JSX tree structure. The model is assumed to encompass all global variables, so in order to guard the model against mutation during rendering, global variable references in the program, such as count, are rewritten to property accesses of a state object, such as state count. Thereby, the render function can be evaluated with a deep copy of the state that dynamically traps mutations with the object.freeze mechanism in JavaScript, applied recursively to the entire model. These deep copies of the model are also appended to the trace of application states to enable back-in-time debugging. Finally, the programming environment also checks that the model does not contain or reference any functions by performing a recursive type of test on all global variables after each event handling process. 2.4, live programming by example. This section describes an extension to live programming that infers live code updates from examples provided by the user at runtime. It is based on the MVU programming model introduced in section 2.2.2. Instead of presenting a concrete implementation, this section first describes the approach conceptually and presents a formalism. Section 2.5 then describes a live programming environment with direct manipulation of string constants as a concrete instance of live programming by example. 2.4.1, live code updates based on output examples. Live programming systems, as described in the previous section, enable program updates at runtime for changes made to the source code. By separating rendering from event handling with the MVU pattern, the application output can be updated in reaction to code changes to provide visual feedback to the developer. Expanding on this idea, the output of the program can also be used by the programmer to make changes to the programmer. This is particularly beneficial for graphical user interface programs, as editing the visible output, e.g. by direct manipulation, is more convenient or intuitive than edits to the generating source. As illustrated in figure 2.7, instead of editing the source code directly, the visible output can serve as a basis for expressing intended changes to the programming. On the one hand, the programmer could provide an example of the intended output that is used by an inference algorithm to synthesize a view implementation. On the other hand, user interface interactions by the programmer, such as direct manipulation of the output, could be applied directly to the generating view code. Depending on the domain and programming language, there are various different programming by example techniques to repair or synthesize a new program whose rendered output partially or fully conforms to the provided output example. 2.4.2, formal definition. Live programming, by example, is applicable to a wide range of applications and programming languages. The potential benefits and limitations depend on the concrete format of the output, the available interactions by the user, and the inference algorithm. However, it is possible to model live programming by example as an abstract system transition that extends the formalism given in Figure 2.5. Figure 2.8 extends the formal definition given in Figure 2.5 with support for live programming by example. Both the program synthesis technique as well as the user intent of supplied examples enable a wide range of different approaches ranging from the simple manipulation of string literals to sophisticated direct manipulation interactions and end-user programming. 2.5. Live programming by direct manipulation of the output. As a concrete instance of live programming by example, this section presents an approach for editing string literals in JavaScript applications through UI manipulation. The implementation is an extension to the programming environment discussed in section 2.3.5. The approach uses a dynamic string taint analysis to track the source location of string constants in the view code. Thereby, the environment enables the programmer to change string constants appearing in the HTML output and infer changes to the original source code. This programming environment serves as a precursor for future systems that allow synthesis of more complex live code modifications by direct manipulation. The source code and a live demo are integrated into the live programming environment described above. 2.5.1 Example Interaction. In order to illustrate how a programmer might use live programming example to change the view code, this section uses a simple interactive application as an example. The GUI of this application consists of an input field and a label. The label shows the entered text, but replaces keywords in the input text according to a fixed rule. This example is inspired by an XKCD comic, number 1031, and has been implemented by several browser extensions. Listing 2.3 shows an implementation. The model is simply the string entered by the user str. The render function returns the user interface and also binds an event handler that changes the model as the user types into the input field. Since this implementation follows the Mvu pattern, the string constant leopard in the source code can be changed to butterfly, and the programming environment immediately re-renders the output accordingly. However, instead of editing the source code directly, this code change can also be performed by direct manipulation of the output, such that the generating string literal in the source code will be modified to match the intended output example. Figure 2.9 shows how the programming environment can be used to achieve this change. First, the programming environment provides a way to halt normal execution and enable a special interaction mode for the application's user interface. This ensures that interactions with the UI are not handled by the application itself, but by the programming environment. As an alternative to introducing a special interaction mode, it may be possible to reserve certain controls for this purpose, e.g. with a special meta key for direct manipulation or by using halo controls. Different forms of direct manipulation may be available, e.g. resizing or reordering via drag and drop. In this example, the text of the static label becomes editable by the user/programmer. Parts of the label text leopard originate from a string literal in the programming source code. Therefore, the string literal is highlighted in the editor, and changes in the user interface will also be applied to the source code. Text parts that do not originate from the source code literals cannot be modified. Any change to the source code causes the output to be re-rendered, so if the word keyboard would appear more than once in the input text, All of its occurrences would be replaced according to the new render function, thereby ensuring consistency between code and output. 2.5.1.1 Dynamic String Origin Tracking. In order to support the interaction outlined in the previous section, the environment needs a mapping of strings in the output to their generating string literals in the source code. This mapping can be obtained by instrumenting the execution such that string values are replaced by custom string objects with origin information. These string objects include a custom implementation of concatenation, substring extraction, replacement, and other common string operators, such that origin information is retained but otherwise behave like regular string values. This form of dynamic analysis is closely related to taint analysis for information flow security. As a first step of the source code instrumentation process, all string literals/constants in the code are replaced by expressions that create custom tagged string objects with both the original string value as well as a unique identifier to track the source code location. Additionally, built-in unary and binary operations are replaced by function calls implementing these operators. While concatenation with the regular plus operator behaves as expected, this instrumentation is necessary to retain the origin information. Due to concatenation and other operators, different parts of a string can originate from different string literals in the code. The origin information therefore includes all subparts of a string alongside the identifier of the generating string literal and offset. JavaScript code that is not part of the program, especially built-in/native code, is not subject to the code rewriting. To ensure correct behavior for application passing tagged strings to uninstrumented functions, JavaScript's metaprogramming facilities, such as proxy and property definitions for symbol.iterator, etc., are used to ensure that these tagged string objects are mostly indistinguishable from regular strings. In particular, tagged string values are wrapped in a proxy that automatically converts tagged strings to primitive strings when no instrumentation is possible or necessary, e.g. for parsing strings as integers. And input events from the DOM passed to event handlers are wrapped in a proxy membrane that transparently converts primitive strings to tagged strings. While this approach preserves program behavior, it is possible for a string to lose its origin information due to built-in JavaScript functions. 2.5.1.2 Programming Environment Integration. The kinds of supported UI interactions depend on the domain and concrete representation of the input. In the context of the live programming environment for JavaScript, the output is a tree of HTML/DOM elements and attributes. With string origin tracking, plain text content, attributes, and element names can potentially contain origin information. The programming environment shown in Figure 2.9 supports two ways of manipulating the output for the purpose of live program synthesis. The developer can either edit the raw HTML code or manipulate text in the graphical user interface. The HTML representation has the advantage that all parts of the output, including element names and attribute keys and values, can easily be modified on a textual level. Manipulation of the visible UI is limited to the plain text content of HTML elements, but allows programmers to perform changes in an intuitive way on the level of the actual output. Given a modified DOM tree, the program synthesis generally follows the following informal algorithm. 1. Determine the previous output based on the current rendering code and application state. 2. Compute the difference between the provided example and the previous output. The modified DOM tree either has new characters inserted, existing characters removed, or both. 3. Check origin information of the modified characters. Modifications to string parts that do not have origin information cannot be handled and will be suppressed. 4. Determine source code location. of the generating string literals using string origin information and a mapping from string literals to AST nodes. 5. Use the source code location and computed offsets to insert or delete characters in the program source code. 6. Evaluate / recompile code and obtain a new rendering method. 7. Render the updated output using the modified rendering code and the current program state. Listing 2.4 shows a simplified JavaScript implementation of the algorithm above when deleting characters. In this case, pard is deleted from leopard in the UI, so the example contains the modified UI that differs from the previous output as rendered with the current program view and application state. The difference is used to determine the originating string literal in the AST of the program and thereby the location in the original source code. According to the difference in the outputs, 4 characters were deleted, so this change is also applied to the program source code. Finally, the program gets recompiled, yielding a new view function, and the output is re-rendered. 2.6. Discussion and future work. This chapter outlined an approach for live programming of event-based GUI applications. In addition to live code updates, this technique also enables back-in-time debugging, runtime version control, and live programming by example as a way to change the code of a running program, including a prototype implementation for direct manipulation of string constants in the user interface. 2.6.1 Live programming for MVU applications. The approach relies on the MVU programming pattern with a stateless view and update component, and a model that encompasses the entire application state. Live code updates may involve added, modified, or removed function definitions. Unfortunately, function values / closures in the application state cannot always be automatically transformed to match the new code. Therefore, closures are currently not allowed in the application state. Restricting the global state in this way limits expressiveness but avoids ambiguity and ensures that code updates do not result in outdated references. More research is necessary to evaluate the design decisions and study how programmers can benefit from live programming for other architecture patterns. Moreover, live programming may lead to inconsistencies in the application state. If the event handling code is updated and execution resumed, input events in the execution history will have been processed by different versions of the same event handler. Therefore, the resulting application state may be inconsistent, i.e. it may differ from the application states produced by either version of the event handler for a restarted and replayed execution. As long as the application state is internally consistent, inconsistencies with past input events are mostly benign and insignificant for the programming experience. However, there could be situations in which resuming execution and replaying events is more desirable for development or debugging. Finally, changes to the initialization code of the program are not reevaluated and do not provide feedback to the programmer. If this change also alters the data type of the application state, the current runtime state may become incompatible with the code and require either manual data migration or a restart of the execution. Future work might also involve common programming language techniques to improve the performance overhead, such as proxy membranes for enforcing immutability and first-order states, copy on write for optimizing back-in-time debugging, and incremental computation for the new output. 2.6.2 Live Programming by Example. The programming environment presented in this chapter supports a simple form of live programming by example, but mainly serves as a precursor for future systems that support more sophisticated program synthesis guided by more flexible forms of direct manipulation. With the presented approach for live programming by example, code updates to the rendering code can be synthesized and applied immediately. However, updates to the event handling code will only affect subsequent events, and therefore, live programming by example, as presented in this chapter, is not directly applicable to the event handling code. A possible solution is to replay past events instead of resuming execution with the existing state. It is not always clear how many events have to be replayed, as replaying all events may not be practical or desirable for long-running applications, and replaying just the last event may not suffice. But future work may expand the live programming environment to enable inference for rendering code as well as event handling code. Changing string literals in the program by manipulating text in the output is a relatively simple implementation of live programming by example, and thereby avoids ambiguities that are common in program synthesis applications. However, more complex live programming by example solutions have to address potential ambiguities with heuristics or manual user intervention. For example, the programming environment might present multiple ranked synthesis candidates for the programmer to choose from. Finally, the approach still needs to be evaluated for larger applications and development tasks, potentially as part of a user study. In JavaScript, there is a beautiful, elegant, highly expressive language that is buried under a steaming pile of good intentions and blunders. Douglas Crockford. Chapter 3. Program Verification for JavaScript. This chapter describes the design and implementation of sVerify, a program verifier for JavaScript. The goal of sVerify is to ensure a comprehensible verification process with quick feedback as part of an integrated programming environment, as well as support for dynamically typed programming idioms in JavaScript that are not well supported by type systems. sVerify is based on SMT solving, but instead of using heuristics for quantifier instantiation, it uses a custom trigger-based quantifier instantiation algorithm. As a result, sVerify requires more explicit annotations to verify some program, but its verification errors are easier to understand and inspect. Finally, this section also presents case studies to illustrate and evaluate how smaller JavaScript programs can be verified with sVerify. 3.1 Overview. The goal of program verification is to statically check programs for properties such as robustness, security, and functional correctness across all possible inputs. For example, a program verifier might statically verify that the result of a sorting routine is sorted and is a permutation of the input. This chapter introduces sVerify, a program verification system for JavaScript. JavaScript, a dynamically typed scripting language, was chosen as target because its broad user base suggests many beneficial use cases for static analysis, and because its availability in browsers enables accessible online demos without local installation. JavaScript programs often include idioms and patterns that do not adhere to standard typing rules. For instance, the latest edition of the JavaScript/Emacs script standard ECMAS script standard introduces promises such that a promise can be composed with other promises and with arbitrary objects, as long as these objects have a then method. Since sVerify does not rely on static types, it can easily accommodate these idioms. JavaScript programs also often use higher order functions. In order to support verification of these functions, sVerify introduces a new syntax to constrain function values in terms of their pre- and post-conditions. Similarly, other JavaScript values such as numbers, strings, arrays, and classes can be used in assertions, including invariants on array contents and class instances. The implementation of asVerify, including its source code and a live demo, are available online. In summary, if a JavaScript program uses features unsupported by asVerify, it will be rejected early. Otherwise, verification conditions are generated based on annotations, and each verification condition is transformed according to a quantifier instantiation algorithm and then checked by an SMT solver. 3.2. asVerify. By supporting a subset of the ECMAScript script / JavaScript, a dynamically typed scripting language, asVerify is unlike existing verifiers for statically typed programming languages. The goal of asVerify is not to support complex and advanced JavaScript features such as prototypical inheritance and metaprogramming, leaving these extensions for future work. Instead, the goal is to support both functional as well as object-oriented programming paradigms with an emphasis on functional JavaScript programs with higher order functions. 3.2.1. Annotating JavaScript with assertions. asVerify extends JavaScript with source code annotations such as functions, pre- and post conditions, loop invariants, and statically checked assertions. These are written as pseudo-function calls with standard JavaScript syntax, while some program verification systems specify these in comments such as ESC/Java. This approach enables a better integration with existing tooling support, such as refactoring tools and syntax highlighters. The assertion language is a subset of JavaScript. It does not support all of JavaScript's semantics. In particular, it is restricted to pure expressions that do not contain function definitions. 3.2.2. Max, a simple example. Listing 3.1 shows an example of an annotated JavaScript program that calls to, requires, and ensures in lines 2 through 5 are only used for verification purposes and excluded from evaluation. Instead of introducing custom type annotations, the standard JavaScript type of operator is used to constrain the possible values passed as function arguments. Due to a bug in line 9, the max function does not return the maximum of the arguments if b is greater than a, violating the post condition in line 5. 3.2.3. Programs and loop invariants. For programs without loops or recursion, static analysis can check various correctness properties precisely. However, the potential behavior of programs with loops or recursion cannot be determined statically. asVerify over-approximated the behavior of the program, i.e., correct programs may be rejected if the program lacks a sufficiently strong loop invariant or pre or post condition, but verified programs are guaranteed to not violate an assertion regardless of the number of iterations or recursive function calls. Listing 3.2 shows a JavaScript function that computes the sum of the first n natural numbers with a while loop. The loop requires annotated invariants for mutable variables, including their types and bounds. Without these loop invariants, the state of I and S would be unknown in line 13 except for the fact that I is less than n is false. However, when combined with the loop invariants, the equality I = n can be inferred after the loop, and thereby the post condition in line 3 can be verified. asVerify internally uses standard SMT theorems for integer arithmetic to establish that the invariants are maintained for each iteration of the loop. There is extensive prior work on automatically inferring loop invariants. Recent research suggests that automatic inference can also be extended to program invariants and specifications. However, this topic is orthogonal to the program verification approach presented in this thesis. 3.2.4. Higher order functions. In order to support function values as arguments and results, asVerify introduces a spec construction in post conditions and assertions. Listing 3.3 illustrates this syntax in lines 7 and 8 of the higher order twice function. The argument f needs to be a function that satisfies the given constraints, and therefore the call site twice parentheses inc comma n and parentheses in line 16 requires asVerify to compare the pre and post conditions of inc with pre and post conditions in line 7 and 8. It is important to note that asVerify implicitly strengthens the stated post condition of inc by inlining its function body x plus 1. Recursive functions are only inlined by one level, so these need to be explicitly annotated with adequate pre and post conditions. For verification purposes, similarly to loop invariants. 3.2.5 Arrays and objects. In addition to floating point numbers and integers, asVerify also supports other standard JavaScript values, such as Boolean values, strings, functions, arrays, and objects. However, asVerify restricts how objects and arrays can be used. Specifically, mutation of arrays and objects is not currently supported, and objects have to be either immutable dictionaries that may strap keys to values or instances of a user-defined classes with a fixed set of fields without inheritance. The elements of an array can be described with a quantified proposition corresponding to the standard array method every. This is illustrated in listing 3.4. Despite these restrictions, it is possible to express complex recursive data structures. Section 3.4 presents examples of such data structures, including user-defined list classes containing sorted integers. 3.2.6 Dynamic programming idioms. JavaScript programs often include functions that have polymorphic calling conventions. A common example is the jQuery library, which provides a function $, whose behavior varies greatly depending on the arguments. Given a function argument, the function is scheduled for deferred execution, while other argument types select and return portions of the current web page. Even standard JavaScript objects use dynamic programming idioms to provide a more convenient programming interface. As mentioned in section 3.1, the latest edition of the ECMAScript standard includes promises and specifies a polymorphic promises.resolve function. This function behaves differently depending on whether it is called with a promise, an arbitrary non-promise object with a method called then, or a non-promise object without such a method. asVerify can accurately express these kinds of specifications in pre and post conditions as shown in listing 3.5, while standard type systems need to resort to code changes such as sum types and injections. 3.3 Implementation. The asVerify prototype implementation is available online. Because the implementation itself is written in TypeScript, a dialect of JavaScript, it can be used in a browser. Indeed, there is a browser-based editor with asVerify checking. Alternative integrations, such as extensions for Vim and Emacs, also exist. The basic verification process and overall design of asVerify is depicted in Figure 3.1. The first step of the process involves parsing the source code and restricting the input language to a subset of JavaScript supported by asVerify. Some of these restrictions may be lifted in future versions of asVerify, such as support for regular expressions or functions with a variable number of arguments. However, other JavaScript features would involve immense complexity for accurate verification due to their dynamic character and their interactions with the rest of the program, such as metaprogramming with eval or new function. Additionally, asVerify does not support features that have been deprecated in newer versions of strict mode JavaScript such as arguments.callee. This outside of functions or with the or the with statement. The parser also differentiates between expressions and assertions. For example, spec can only be used in assertions, while function definitions can only appear in the actual program implementation. During the second step, scope analysis determines variable scopes and rejects programs with scoping errors and references to unsupported global objects. In addition to user-provided definitions, it includes a whitelist of globals supported by asVerify, such as array, math, and console. The analysis also takes mutability into account. For example, mutable variables cannot be referenced in class invariants. In the old X syntax, in a post condition requires X to be a mutable variable. The main verification step is implemented as a traversal of the source program that generates verification conditions and maintains a verification context. Most notably, the verification context includes a logical proposition that acts as a precondition and a set of variables with unknown values. Generated verification conditions combine this context with an assertion, such as a function postcondition. Figure 3.2 illustrates this process for a simple example. The verification condition shown on the right checks whether the precondition and the translated function body imply the postcondition in line 4. Section 4.5 describes the verification rules in more detail. The verification condition is then transformed with a quantifier instantiation procedure. As illustrated by figure 3.3, quantified propositions and verification conditions need to be instantiated with concrete values in order to determine satisfiability of the formula. Quantifiers are instantiated based on matching triggers, and remaining quantifiers are then erased from the proposition. The resulting quantifier-free proposition can be checked by SMT solving, ensuring that the verification process remains predictable. Predicable. However, this approach to quantifier instantiation requires the programmer to provide explicit triggers as function calls. Alternatively, the trigger-based quantifier instantiation can be skipped and the proposition passed directly to the SMT solver, which internally performs instantiations based on heuristics. The final step of the verification process involves checking the verification condition with an SMT solver, such as Z3 or CVC4. If the solver cannot find a solution for the negated verification condition, i.e. if the solver cannot refute the proposition, verification succeeded. Otherwise, the return model includes an assignment of free variables that acts as a counterexample. 3.4, Evaluation. A comprehensive evaluation of asVerify for real-world projects would require a stable and mature implementation and immense engineering effort. However, it is also possible to illustrate potential benefits and limitations with limited case studies, such as verified implementations of well-known algorithms. Therefore, this section presents and discusses a series of non-trivial programs and verifies their functional correctness. 3.4.1 Reversing an ascending list. This example involves a class definition for lists of integers and a reverse function. By adding annotations about pre- and post-conditions, asVerify can statically verify that reversing an ascending list yields a descending list. Finally, first, the program defines the class intList, as a linked list with head and tail. The class invariant of intList ensures that the current element, head, is a number and that the linked list, tail, is also an intList. Instead of introducing a second class for empty lists, this program uses null to represent empty lists. In order to verify the reverse function, it is necessary to define what it means for a list to be ascending. In isVerify, these definitions, so-called predicates, are written as standard JavaScript functions despite being used solely for verification purposes. The body for this function determines whether a given list contains ascending integers. The precondition in line 12 ensures that arguments are either integer lists or null, which represents the empty list. And the postconditions in line 13 and 14 restrict the function to return Boolean values and not invoke side effects. These annotations are primarily for checking the recursive call of isAscending in line 17. The remainder of the program will use the isAscending predicate function as a definition for ascending integer lists. In other verified languages, such as Daphne, isAscending would correspond to a ghost function, but isVerify does not currently differentiate between predicates and regular functions. The definition of isDescending follows accordingly. isVerify does not currently support mutation of class instances. Therefore, the main algorithm for reversing the list is purely functional. Instead of modifying the list supplied as argument, it uses a recursive helper function, reverse helper, to traverse the list and build up a reversed list. The implementation of the reverse function is shown below. Most importantly, it requires the argument to be an ascending integer list, and it ensures that the result is a descending integer list. As shown in lines 34 through 36, an empty list as input argument results in an empty list as return value. While it seems obvious that an empty list is descending, isVerify requires an explicit hint, as shown in line 35, to unfold the definition of isDescending for the argument null. This function call does not contribute to the result, it is merely a trigger for the underlying SMT solver and the quantifier instantiation algorithm. Similarly, the preconditions of reverse helper require that list.tail is ascending, which necessitates triggers that expand the definition of isAscending in lines 38 through 40. Finally, the recursive helper function, reverse helper, implements the actual reverse algorithm. A reverse list is accumulated in revList, initially just null, and the pivot is the current number, not smaller than the descending numbers is in revList, and not greater than the ascending numbers in the remaining list. Again, pre- and post-conditions are used to specify these constraints, and triggers are used to unfold the definitions of isAscending and isDescending for concrete arguments. The overall program can be verified with isVerify, and thereby the functional correctness of the reverse function statically checked. Out of 64 total lines in the source code, 40 are primarily for verification purposes. This includes the class invariant, annotated pre- and post conditions, the definitions of isAscending and isDescending, and function calls in the code that serve as triggers. 3.4.2 Merge Sort Algorithm. As a slightly more complex example, this section includes an implementation of merge sort and verifies that returned lists are sorted. The algorithm is based on linked lists of integers analogous to the class definition used for the reverse algorithm in section 3.4.1. Additionally, the merge sort algorithm defines a predicates is sorted as a JavaScript function that is identical to the isAscending definition in section 3.4.1. The merge sort algorithm divides the input list into two partitions that are sorted independently and then merged. In order to split and return an integer list with two partitions as a single value, the program introduces a second class definition that represents a pair of two integer lists. The partition function takes the original list as first argument and then accumulates two lists recursively while alternating between appending to the first or second list. The merge routine is the most complex part of the algorithm. Given two lists, if neither of them is empty, the method will compare the head elements and then select the lesser element. All remaining elements will be recursively merged such that prepending the selected elements results in a sorted list. The post conditions explain this behavior, and triggers are used to unfold the definition of is sorted. Finally, the main function simply returns the given list if it is empty or has just a single element, and otherwise uses partition, recursion, and merge to implement the merge sort algorithm. In summary, about 48 out of a total 96 lines are verification annotations, including invariants, pre and post conditions, and the predicate function is sorted. 3.4.3, custom generic lists class. While the previous two examples uses a custom class specifically for lists of numbers, it is also possible to define a list class that can be parameterized by a generic invariant that holds for each element. Here, the field each is a function value that acts as a predicate, i.e., it is a pure Boolean valued function that is used for verification returns true for all elements in the list. Mapping a function f over a list results in a new list where each element corresponds to the result of f. In this example, the current list predicate, lst.each, has to satisfy the precondition of f. Additionally, there is a third argument, new each, that represents the new predicate of the list after mapping. Therefore, the postcondition of f needs to be at least as strong as new each. To simplify reasoning, the pseudo call pure in the postcondition ensures the absence of side effects. It is important to note that function calls in an assertion context are uninterpreted. So the call new each y in line 21 only refers to the function return value, but does not actually invoke the function. It would be possible to rewrite the previous two examples using this parameterized list class. This demonstrates how generic data structures can be expressed with asVerify, analogous to parameterized type systems. Theorem 3.4.4, theorems and proofs written in JavaScript. Despite being a program verifier, asVerify can also be used to write general theorems and proofs. As previously shown in listing 3.2, while loops with loop invariants are analogous to simple induction proofs over natural numbers. More generally, spec can be used to reify propositions instead of describing computation results. In particular, the post condition need only describe the return value. It can also state a proposition such that a value that satisfies the function specification acts as a proof of this proposition. Analogous to the Curry-Howard isomorphism, such a function value can then be supplied as argument to higher order functions to build up longer proofs. It is important to note that asVerify does not currently check whether recursive functions and loops terminate. Therefore, asVerify can only prove partial correctness and not total correctness. If an annotated function is evaluated to completion, its post condition holds, but theorems proved with asVerify do not apply to non-terminating programs. Future work or external termination checkers could enable asVerify to prove total correctness. For an example, the following listing includes a proof written in JavaScript showing that any locally increasing integer ranged function is globally increasing. This example was previously used to illustrate refinement reflection in Liquid Haskell. Here, f is an arbitrary function from non-negative integers to integers, and prooff inc is a function argument that is not used for computation. Instead, a function value that satisfies the spec in lines 5 through 7 is a proof that f is monotonous for any non-negative x. Additionally, the arguments n and m are integers with n less than m. The overall function prooff mono establishes fn is less than or equal to fm with an induction proof written as recursion with prooff inc invoked at each step. The function prooff mono can now be used to show fn is less than or equal to fm for a concrete function f. The example below shows a definition of the Fibonacci function fib and a proof that fib is increasing. It is now possible to show fib n is less than or equal to fib m for arbitrary n and m with n less than m by passing fib and proof fib inc into proof f mono. 3.5 Future work and conclusions. This chapter described an approach for static verification of dynamically typed JavaScript programs. The implementation as Verify supports both dynamic programming idioms as well as higher order functions. Internally, the verifier relies on a bounded quantifier instantiation algorithm and SMT solving, yielding concrete counterexamples for verification errors, while as Verify enables verification of non-trivial programs such as merge sort. It lacks termination checking and support for object-oriented programming. However, it would be possible to combine it with an external termination checker for total correctness, and to extend it with reasoning about the heap, such as regions or dynamic frames. Finally, while the approach presented in this chapter is purely static, future work might use runtime checks to enable sound execution of programs that are not fully verified. This idea is also used for hybrid and gradual type checking, and has recently been adapted to soft verification and gradual verification. Beware of bugs in the above code. I have only proved it correct, not tried it. Donald Knuth. Chapter 4. Formal development of program verification with Lambda S. In order to clarify the approach of sVerify and reason about its properties, this chapter introduces a formal development of an idealized JavaScript-inspired, statically verified, but dynamically typed language, Lambda S. The verification rules of Lambda S are defined in terms of verification conditions whose validity is checked with a custom decision procedure. Therefore, this chapter first defines the class of logical propositions and axiomatizes their validity, then describes the decision procedure, including quantifier instantiation, and finally gives the syntax and semantics of Lambda S and shows that its verification rules are sound. The definitions, axioms, and theorems in this section are also formalized in the Lean Theorem Prover. The source code of formal development, including definitions, axioms, and theorems, can be found in Appendix A, and the full proof is available online at github.com/fjj/isverify-theory. Additionally, this chapter also includes a brief comparison with static refinement types, refined base type, and dependent functions types can be translated to lambda s annotations, and while a full proof is beyond the scope of this thesis, the translated lambda s program is presumably verifiable if the original program is well typed. This suggests that sVerify is at least as expressive as a language with refinement types. 4.1 Overview. This chapter formally defines lambda s, a JavaScript-inspired dynamically typed language. Functions in lambda s are annotated with pre- and post-conditions, rendered as logical propositions. These propositions can include unary and binary operators, refer to variables in scope, denote function results with uninterpreted function calls, and constrain the pre- and post-conditions of function values. The verification rules for lambda s involve checking verification conditions for validity. This checking is performed by an SMT solver augmented with decidable theories for linear integer arithmetic, equality, data types, and uninterpreted functions. The key difficulty is that verification conditions can include quantifiers, as function definitions in the source program correspond to universally quantified formulas in verification conditions. Unfortunately, SMT solvers may not perform the right instantiations, and therefore quantifiers imperil the decidability of the verification process. In order to ensure a decidable and predictable verification process, lambda s employs a bounded quantifier instantiation algorithm, such that function calls in the source program act as hints, triggers, that instantiate universal quantifiers. The algorithm only performs a bounded number of trigger-based instantiations and thereby avoids both brittle instantiation heuristics and infinite matching loops. Using this decision procedure for verification conditions, it can be shown that verification of lambda s is sound, i.e. verifiable. Lambda s programs do not get stuck. 4.2 Logical Foundation. Figure 4.1 formally defines the syntax of proposition terms, values, and environments. Propositions can use terms, connectives, symbols, and universal quantifiers. Here, terms are either values, variables, unary or binary operations, or uninterpreted function calls. Finally, values include Boolean and integer constants, as well as closures, which are opaque values that will be explained in section 4.4. Instead of defining validity of propositions in terms of an algorithm, such as SMT solving, this formal development uses an axiomization of the validity judgment. These axioms are mostly standard but are listed here explicitly because they form the foundation for both the mechanized lean proof as well as the subsequent definitions and theorems in this chapter. The term true is trivially valid. Validity of conjunctions and disjunctions follow standard inference rules. The following axioms for negation assume that valid propositions do not include contradictions and that the law of the excluded middle holds. For convenience, a notation of implication can be defined in terms of disjunction and negation. There is no evaluation relation for terms. Instead, equality of terms is defined with a selection of axioms. For example, a standalone term is considered valid if it equals true. Equalities involving unary and binary operators are axiomatized in terms of a partial function. The propositions pre-1 and pre-2 can be used to reason about the domain of theta, i.e. the values for which certain operators are defined. Similarly, the constructs pre-fx and post-fx in propositions denote the pre and post condition of a function f when applied to a given argument x. However, in contrast to pre-1 and pre-2, the logical foundations do not contain axioms for pre and post. The interpretation of pre and post is instead determined by their use in the generated verification condition. A universally quantified proposition is true for all values and can be instantiated with any term. A valid proposition is not necessarily closed. In fact, free variables occurring in a proposition are assumed to be implicitly universally quantified. Substitution in terms of propositions can be expressed in terms of an environment or mapping to variables. An environment is a model for a proposition if the substituted proposition is valid. This definition of models is unconventional, but it facilitates the subsequent formal development. It is important to note that this validity judgment may not be decidable for all propositions due to the use of quantifiers. So in addition to this validity judgment, this formalism also introduces a notion of satisfiability by an SMT solver. Proof. SMT solving is not decidable for arbitrary propositions, but the QF-UFLIA fragment of quantifier-free formulas with equality, uninterpreted function symbols, and linear integer arithmetic is known to be decidable. Therefore, SMT solving terminates for all inputs, and its results can be assumed to be consistent with the axioms above. 4.3. Quantifier instantiation algorithm and decision procedure. As described above, the verification of lambda s involves checking the validity of verification conditions that include quantifiers. Quantifier instantiation in SMT solvers is an active research topic and often requires heuristics or explicit matching triggers. However, heuristics can cause unpredictable results, and trigger-based instantiation might lead to infinite matching loops. This section describes a bounded quantifier instantiation algorithm that avoids matching loops and brittle heuristics, thus enabling a predictable decision procedure for verification conditions. The syntax of verification conditions P used in verification rules is similar to the syntax for propositions, but universal quantifiers in verification conditions have explicit matching patterns to indicate that instantiation requires a trigger. Accordingly, the construct call x is introduced to act as an instantiation trigger that does not otherwise affect validity of propositions, i.e. call x can always be assumed to be true. Intuitively, call x represents a function call or an asserted function specification for all x dot call x goes to P corresponds to a function definition or an assumed function specification. For the trigger, call x, x denotes the argument of the call. The callee is omitted as triggers are matched irrespective of their callees by the instantiation algorithm. The complete decision procedure for VCs, including quantifier instantiation, is shown in figure 4.2. To make the definition more concise, it is helpful to first consider defined contexts. For fragments of a VC with positive and negative polarity regarding negation. Using this definition, the set of call triggers in negative positions can be defined as the set of triggers for which there exists a context with negative polarity. The procedure lift plus matches universal quantifiers in positive and existential quantifiers in negative positions. In both cases, an equivalent VC without the quantifier can be obtained by renaming the quantified variable to a fresh variable that is implicitly universally quantified. It is important to note that the matching pattern call y of a universal quantifier now becomes a part of an implication, thereby available to instantiate further quantifiers. The lifting is repeated until no more such quantifiers can be found. The procedure instantiate once performs one round of trigger-based instantiations, such that each universal quantifier with negative polarity is instantiated with all available triggers in negative position. All such instantiations are conjoined with the original quantifier. Both lifting and instantiation are repeated for multiple iterations by the recursive instantiate procedure. As a final step, erase removes all remaining triggers and quantifiers in negative positions. The overall decision procedure performs n rounds of instantiations, where n is the maximum level of quantifier nesting. The original VCP is considered valid if SMT solving cannot refute the resulting proposition. VCSP can syntactically include both existential and universal quantifiers in both positive and negative positions. However, VCs generated by the verifier have existential quantifiers only in negative positions. Theorem 2. Decision procedure termination. If P does not contain existential quantifiers in negative positions, the decision procedure P terminates. Proof. The lift plus function eliminates a quantifier during each recursive call and therefore terminates when there are no more matching quantifiers in the formula. Instantiate once and erase are both non-recursive and trivially terminate. Since the maximum level of nesting is finite, P performs only a finite number of instantiation rounds with existential quantifiers only in negative positions. The erased and lifted result is quantifier free. So according to Theorem 1, the final SMT solving step also terminates. It is now possible to compare the axiomatized validity judgment for propositions with the decision procedure for verification conditions by translating the VCP to a proposition without triggers or matching patterns. Definition 5, proposition translation. Prop P denotes a proposition such that triggers and matching patterns in P are removed and existential quantifiers for each x dot P translated to not for all x dot not prop P. Theorem 3, quantifier instantiation soundness. If P has no existential quantifiers in negative positions, then P implies prop P. Proof. With axiom 15, it can be shown that lift plus preserves equisatisfiability. Additionally, conjuncts inserted by instantiate once could also be obtained via classical not trigger-based instantiation using axiom 14. Furthermore, since erase only removes quantifiers in negative positions and triggers that are inconsequential for validity, the resulting propositions are implied by the original non-erased VC. Finally, with existential quantifiers only in negative positions, the erased and lifted result is quantifier free. Therefore, Theorem 1 can be used to show that a valid VC, according to the decision procedure, is also valid without trigger-based instantiation, QED. 4.4, syntax and semantics of lambda s. Figure 4.3 defines the syntax of lambda s. Values v are either integer or Boolean constants, or closures consisting of a function definition and an environment as previously defined in figure 4.1. Expressions e are assumed to be in a normal form, such that each step of the computation looks up values in the environment and augments the environment with the result. Function calls are processed with a call stack configuration, k, that resumes once the callee finished its computation with a value. This formalism avoids substitution in expressions and assertions in order to simplify subsequent proofs. Function definitions in lambda s are written as let fx rec r ends s equal e1 and e2 with an annotated precondition r and postcondition s. These annotations can include terms such as constants, variables, and uninterpreted function calls, as well as logical connectives and function specifications. As an example, The following JavaScript function uses as verify annotations to specify its pre and post conditions. Function inc x, open bracket, requires number.isInteger x, semicolon, ensures result goes to number.isInteger y and result greater than x, semicolon, return x plus 1, semicolon, close bracket. The same annotated function could be expressed in lambda s as follows. Let inc x rec is int x ends is int inc x and inc x greater than x equal let y equal x plus 1 in return y in ... Since lambda s is a pure functional language, the post condition can refer to the function result with an uninterpreted invocation such as inc x instead of introducing a variable binding such as result above. The operational semantics of lambda s is specified by a small step evaluation relation over stack configurations k as shown in figure 4.4. Most noteworthily, the callee function name is added to the environment at each call to enable recursion, and function pre and post conditions are not checked or enforced during evaluation. The evaluation of a stack configuration terminates either by getting stuck or by reaching a successful completion configuration. 4.5 Program verification. The verification rules of lambda s are inductively defined in terms of a verification judgment, PEQ, as shown in figure 4.6. Given a known precondition P and an expression E, a verification rule checks potential verification conditions and generates a postcondition Q. This postcondition contains a hole for the evaluation result of E as shown in figure 4.5. Since lambda s is purely functional, P still holds after evaluating E, so Q corresponds to the marginal postcondition, and P and Q hole corresponds to the strongest postcondition. For simplicity, the formalism follows the convention that the free variables of P, denoted FVP, must be exactly the set of variables in scope at E. As an example, a unary operation such as let y equals special x in E is verified with the rule VC unop. It requires x to be a variable in scope, i.e. a variable that is free in the precondition P. To avoid name clashes, the result y should not be free. Additionally, the VCP pre-special x needs to be valid for all assignments of free variables such as x. This check ensures that the value of x is in the domain of the operating special, the rules VC binop, VC if, etc. follow analogously. For function applications, fx, an addition call x, trigger is assumed to instantiate quantified formulas that correspond to the function definition or specification of the callee. The most complex rule concerns the verification of function definitions, such as let fx rec r ends s equal e1 and e2. Here the annotated precondition r, the specification of f, and the marginal postcondition q1 fx together have to imply the annotated postcondition f. Any recursive calls of f appearing in its function body will instantiate its non-recursive specification, while subsequent calls of f and e2 will use a post condition that is strengthened by the generated marginal post condition. This corresponds to expanding or inlining the function definition by one level at each non-recursive call site. The special syntax spec rec rns s, as used in verification rules, user provided pre and post conditions, is a notation that desugars to a universal quantifier when appearing in verification conditions. That is, in reference to notation 3, that is, if a function call instantiates this quantifier, the precondition R of the spec satisfies the precondition of F, and the postcondition S of the spec is implied by the postcondition of F. For a concrete function call, this means that R needs to be asserted by the calling context, and S can be assumed at the call site. 4.6, soundness. Based on the decision procedure and the verification rules described in the previous sections, it is possible to show that verified programs evaluate to completion without getting stuck. While annotated assertions are not directly enforced by the operational semantics, the preconditions of operators have to be satisfied and can be arbitrarily complex. Therefore, this soundness property also ensures that annotated assertions such as postconditions hold during evaluation for concrete values of free variables. First, it is important to note that quantifiers and generated VCs only appear in certain positions. Lemma 1. Proof. All VCs in the verification rules shown in figure 4.6 are implications of the form P goes to Q. In each of these implications, there are no existential quantifiers. Q, as user-supplied postconditions, S have no existential quantifiers. Additionally, all propositions P on the left-hand side have existential quantifiers only in positive positions. Since existential quantifiers in marginal postconditions are always in positive positions, QED. From Lemma 1 and Theorem 2, it follows that verification always terminates, ensuring a predictable verification process. As mentioned in section 4.2, the axiomatization of logical propositions does not include evaluation and treats terms T as uninterrupted symbols rather than function calls. However, for a proof of verification soundness, it is necessary to establish equalities about function application for a given closure and argument value. Similarly, axioms about pre-effects and post-effects can be added for concrete values of f and x. Based on these axioms, definitions, and verification rules, it can now be shown that verifiable expressions evaluate to completion without getting stuck, i.e. all reachable configurations either terminate normally or can be further evaluated. Theorem 4, verification safety proof. Due to the complex quantifier instantiation of the decision procedure, verification safety is first proven for a verification judgment that is similar to the one in figure 4.6, but uses the undecidable validity prop P without quantifier instantiation rather than the decision procedure P. The verification safety proof for this alternate judgment uses a standard progress/preservation proof strategy, where the notion of verifiability is extended to stack configurations such that a given routine runtime stack is considered verifiable if at each stack frame the expression is verifiable with the translation of theta as precondition. With Theorem 3, it follows that soundness of this verification judgment also implies soundness with trigger-based quantifier instantiation. A complete proof is available at https://github.com/levjj/asverify-theory/QED. 4.7 Extensions. The language lambda s includes higher order functions but does not address other language features supported by asverify, such as imperative programs and complex recursive data types. 4.7.1 Imperative programs. Extending lambda s for imperative programs would entail syntax, semantics, and verification rules for allocating, mutating, and referencing values stored in the heap. Most noteworthy, loops and recursion invalidate previous facts about heap contents and therefore require precise invariant. To simplify reasoning, it is useful to distinguish heap manipulating functions from pure functions. In asverify, the pseudocall pure appearing in a postcondition indicates that the function is prohibited from manipulating the heap. A formal development might introduce separate syntactical classes for these types of functions. In order to express invariants for heap manipulating code, such as functions and loops, as verify additionally introduces a syntax old x that denotes the previous value of a variable. This enables annotations such as x equal old x to confine the effects of heap manipulating code to certain mutable variables. This issue can also be addressed with segmentation logic, effect systems, regions, and dynamic frames. 4.7.2 Recursive data types and classes. The core language Lambda S can be extended to support classes. As shown in figure 4.7, these classes are immutable and more akin to recursive data types as they do not support inheritance. Each class definition consists of an ordered sequence of fields and an invariant S that is specified in terms of a free variable this. The class invariant can be used to express complex recursive data structures such as the parameterized linked list shown in section 3.4.3. The class invariant has to be instantiated for concrete instances of the class. So a trigger access X is inserted into verification conditions at each field access, similarly to call X trigger for function calls. However, unlike function definitions, class definitions D are global. Therefore, VCs need to be augmented with a preamble such that for each class CFD in S, the following quantifier is assumed. For all x.access x goes to x instance of C goes to top bar x has FD and S bracket this implies x close. Instantiating this quantifier with an access x trigger yields a class invariant S with this replaced by the accessed object, as well as a description of the field's top bar FD. 4.8 Comparison with refinement types. The verification rules shown in figure 4.6 resemble static typing rules. This section provides a brief comparison of the program verification approach with static type checking by defining an automatic translation of types to Lambda S, annotations, and examining concrete examples. The results suggest that as verify is at least as expressive as systems such as Liquid Haskell, but a comprehensive formalization of dependent type systems and a formal proof to determine their expressiveness is beyond the scope of this thesis. The language Lambda T is similar to Lambda S, but with type annotations instead of pre and post conditions. Figure 4.8 sketches an excerpt of such a language. Here a type is either a dependent function type or a refined base type where refinements are consistent with specifications in Lambda S. The typing rule for function definitions is shown in figure 4.8. This annotated return type T might refer to the function argument in order to support dependent types, but other free variables and refinements can break hygiene. So TFN restricts free variables in user-provided types Tx and T accordingly, and also prevents name clashes with previously defined symbols f and x. For checking the function body T1, the type environment T is augmented with types for x and the function f itself to enable recursion. Instead of checking the post condition with the verification conditions, as in Lambda S, the computed type T1 for the function body is compared with the annotated return type T by checking subtyping. Type checking then proceeds with the expression T2. The subtyping relation is also shown in figure 4.8. Most importantly, subtyping of refined base types requires checking an implication between the refinements, and it requires translating the type environment T to a logical formula extra T, where function types translate to the function specifications with the spec syntax. Were presented and discussed in Chapter 3 and 4 respectively. However, in order to use verification as part of an iterative development process, the verifier also needs to provide useful and comprehensible feedback to the programmer. Simple error messages are often not sufficient to explain verification errors to the programmer, but counterexamples in the form of executable tests can serve as an explicit witness and enable step-by-step debugging of the relevant parts of the code with concrete variable values. This chapter describes how the sVerify program verifier can be extended with a test generation algorithm, and it discusses how these generated tests assist the programmer in determining whether a verification issue corresponds to a bug in the code or an insufficient annotation or invariant. The implementation of the test generator is already merged into sVerify itself and serves as a basis for an integrated development and verification environment that will be discussed in Chapter 6. 5.1 Overview. Figure 5.1 illustrates the basic verification process. The generation of verification conditions and the SMT solving procedure are described in more detail in section 3.3, but this chapter extends this process with automatic counterexample generation and testing. In summary, the verification step traverses the entire source program. At each statement and expression, the current verification context is used to generate verification conditions and augment the context for subsequent statements and expressions. Specifically, the verification context includes a logical proposition that acts as precondition, a set of free variables with unknown values, and a synthesized test with holes. Each returned verification conditions consists of such a context and an assertion to check, such as a function postcondition. The next step of the verification process involves checking the verification condition with an SMT solver. If the solver cannot refute the proposition, the verification succeeded. Otherwise, the return model includes an assignment of free variables that acts as a counterexample. Such a model can then be combined with the synthesized partial testing. Inserting concrete values into the holes of the test yields an executable counterexample that can be evaluated by a test runner. The test result provides useful feedback such as dynamic assertion violation and enables inspection with interactive step-by-step debuggers and other tools. 5.2 Verification errors and assertion violations. The purpose of automatic test generation is to provide better feedback about failed verification conditions. In contrast to simple Boolean expressions, function specifications expressed with a spec syntax, as used by the twice function in listing 5.3, cannot be checked dynamically for all values at the point of the assertion. Instead, the function argument is wrapped in a contract that enforces the specified pre- and post-condition for each subsequent call in the scope of the spec. 5.3.2 Contract checking. Listing 5.4 illustrates how the twice function can be transformed to enable dynamic checking of function specifications. The code shown here is slightly simplified. In particular, it does not collapse wrappers to avoid repeated and redundant wrapping. It is important to note that assuming and asserting a function specification result in a different transformation. In this example, the twice function and its returned inner function are assumed to adhere to their function specifications, but the function argument f is not trusted to behave correctly when invoked with correct arguments. Therefore, the postcondition of f is dynamically checked, but its precondition assumed, and conversely, the preconditions of g and the spec in the postcondition of twice are enforced, but their postconditions are not. Incidentally, this mechanism is similar to blame assignment. The example in listing 5.3 only includes first and second order functions, but it is also possible for a function specification with spec to occur within another spec. In that case, the transformation of function specifications is applied recursively, i.e. the inner wrapping code gets executed as part of the dynamic checks of the outer wrapper. This technique of dynamically checking assertions is only used in generated counterexample test, but it could also be adapted to support sound execution of partially verified programs, similar to soft verification and gradual verification. 5.4 Synthesis counterexample values. As shown in figure 5.1, if the SMT solver refutes a verification condition, it returns a model that assigns values to free variables in the verification condition. In order to generate executable tests, these values have to be translated from an SMT internal format to valid JavaScript expressions that can be inserted into the testing code. For opaque JavaScript values, such as undefined, null, true, and false, this translation is trivial. Numeric values in JavaScript conflate integers and floating point numbers, and therefore are represented as either integers or real numbers in the SMT format in order to support both integer semantics for array indexing as well as floating point semantics for arithmetic operators. Modern SMT solvers such as Z3 and CVC4 contain theories for strings with support for indexing and substrings. Therefore, these JavaScript strings can be directly represented as SMT strings. sVerify provides limited support for object-oriented programming by means of immutable classes without inheritance and only trivial constructors. As an example, listing 5.5a shows a class definition with a method m containing an incorrect assertion. Adding a sufficiently strong class invariant to a would let verification succeed. In the generated test shown in listing 5.5b, this is renamed and initialized with a constructor invocation according to the SMT model. For plain JavaScript objects / records and arrays, the test generation follows a similar strategy. Due to the modeling of data structures as immutable values instead of heap references, the generated counterexamples deviate from standard JavaScript semantics with regards to aliasing. Similarly, counterexamples with cyclic references in data structures are not currently supported. In order to generate counterexamples for higher order functions, the test generator has to synthesize function values. Program synthesis is an active research topic with various different approaches and techniques, but sVerify only supports a limited synthesis for the purpose of test generation. In particular, the synthesis of function values is limited to pure functions that map primitive argument values to return values. Thereby, the function can be expressed as a series of conditionals. Listing 5.6 shows a generated test for the violated precondition of f null in line 9 of listing 5.3. Here, a synthesized function value is assigned to f and then wrapped according to the specification in line 7 of listing 5.3, resulting in an assertion violation when invoked with null. The synthesized function is based on a partial mapping and might include constants picked non-deterministically by the SMT solver. Therefore, the synthesized function may not adhere to the function specification when invoked with other arguments not included in the SMT mapping. This is why the synthesized function f returns a seemingly random number, such as 9174, for the argument 3, but does not return correct values for other arguments. 5.5. Generating counterexample function calls. When asserting function specifications, the specification is transformed to a wrapper in the generated test. However, without subsequent calls, the test would simply end without triggering an assertion violation. Therefore, the test generator also needs to synthesize a violation-provoking call after installing the wrapper for the asserted specification. As an example, the post condition of the twice function in listing 5.3 does not hold because the inner post condition in line 12 is not satisfied by the returned function. Listing 5.7 shows a simplified generated test with a synthesized function value for f, the original function body of twice, assuming f null is replaced by fn, and a wrapper for the function specification in the post condition of twice. Additionally, the generated test also includes a synthesized function call g-2 that causes an assertion violation in line 15. The argument values for this violation-provoking function call are determined based on the SMT model. 5.6. Conclusion and future work. Program verifiers enable expressing and checking various correctness properties, but understanding and debugging resulting verification errors can be difficult. Therefore, this chapter outlined an approach for automatically generating executable counterexamples. Program verification with asVerify is based on SMT solving. This has the advantage that the SMT solver also provides a concrete model for invalid verification conditions, i.e. it finds an assignment of free variables to values that serve as a counterexample. The raw output of the SMT solver includes low-level verification details, so it needs to be translated to the level of the original source program to be usable by the programmer. Testing can be a very effective way to present and explain these counterexamples, as it directly concerns the execution of the code, and it also enables the use of existing development tools such as a step-by-step debuggers. Therefore, the asVerify program verifier was extended to generate tests as executable counterexamples for invalid verification conditions. In generated tests, annotations such as invariants, pre- and post conditions are converted to dynamically checked assertions and contracts. Additionally, functions, arrays, and complex objects in the SMT model are translated to JavaScript expressions. This chapter presents a solution for synthesizing functions as part of counterexamples such that the synthesized functions always return the same result for the same argument values. Support for imperative programs is limited, as this simple synthesis method does not generate functions that manipulate global state or object graphs with cyclic references. Related work on program synthesis already investigated these issues, so future extensions to the test generator could incorporate a more sophisticated program synthesis technique. As explained in section 5.2, not all failed verification conditions are caused by actual bugs in the code. It is possible for a correct program to be rejected by the program verifier due to lacking annotations, such as a loop invariant or postcondition. This poses a question to test generation, as it could either result in a non-failing test that runs without assertion violations or a failing test that uses values from the verification logic instead of fragments from the actual source code. Both of these approaches offer different benefits, so as Verify implements a compromise solution, future research might help to guide the design of automatic test generators in the presence of this trade-off. Finally, the design of the test generator has to take into account whether and how generated tests are presented to the user. One option is to manage generated tests like regular unit tests. Thereby, these tests could be debugged with existing development tools and even added to an existing test suite, but it would also expose automatically generated code to the programmer that may not be very readable. Instead of displaying generated test code directly, the test generator described in this chapter is used internally as part of an integrated development and verification environment that is described in the following chapter. So much of the way we work with systems today is derived from pencil and paper. Even whilst we are at the computer, we are still thinking in pencil and paper. There is an incredible opportunity now to rethink how we think about systems. Brett Victor, Chapter 6, Integrated Development, Verification Environments. This chapter describes a programming environment for verification that enables interactive inspection and experimentation with live feedback. Based on the program verifier described in Chapter 3 and the automatic test generation in Chapter 5, the programming environment integrates the code editing, verification, and debugging. In particular, it explains verification errors with concrete values that serve as counterexample. It lets programmers step through the relevant parts of the code leading up to the verification error with these values. And it enables live edits to assertions and assumptions of verification conditions. Thereby, the programmer can determine the cause of verification issues and narrow down their scope without having to manually add assert statements to the code. This kind of environment integration is analogous to step-by-step debuggers that let programmers explore the execution state of a program without having to resort to printf debugging. Additionally, this chapter also describes an online user study where participants solved small programming and verification tasks and answered survey questions to evaluate how the development and verification features of the environment were used and perceived. 6.1 Overview. Program verifiers, such as this Verify, enable the programmer to express correctness properties in an expressive assertion language, often based on first-order logic. However, the verification process for these assertions is relatively complicated and verification issues can become difficult to understand. In these cases, simple feedback mechanisms in the form of error messages may not be sufficient to help the programmer resolve these verification issues. In order to improve the programmer experience for verified programming, this chapter presents IDVE, an integrated development and verification environment that lets user interactively inspect and debug verification issues. The goal of IDVE is to support programmers with an interactive interface for understanding and interactively manipulating verification conditions. An essential component of this integration is the automatic generation of counterexamples for verification errors as described in Chapter 5. As a brief overview, it is useful to illustrate the scope and goals of the proposed programming environment with an example shown in Figure 6.1. Here, a JavaScript function, ABS, is annotated to indicate that its result is always non-negative. However, due to a bug in the ABS function, the result might be negative, violating the post condition in line 3. The prototype implementation of the integrated development and verification environment, abbreviated as IDVE, helps the programmer identify verification conditions and inspect potential verification errors. Figure 6.1 does not show the full programming environment, but it illustrates how symbols next to the line numbers are used to indicate verification conditions. Hovering over these marks with the mouse cursor display additional details similar to type environments. For valid verification conditions, IDVE also displays counterexample values as editor pop-ups. For example, it displays -1 as a value for the function argument n that causes a violation of the post condition. Additionally, IDVE also enables programmers to inspect verification conditions by opening an interactive inspector panel that lets users inspect, add and remove assumptions and assertions similar to watch expressions in an interactive debugger. Thereby, the verification inspector allows programmers to explore the verifier state without manually adding assert statements to the code, analogous to how interactive debuggers let programmer avoid printf debugging. The environment also includes an integrated debugger for the automatically generated test cases that lists variables in the scope, shows the current call stack, and allows step-by-step debugging. Finally, the environment and its usability for developing verified programs was evaluated with a user study with 18 participants that have at least basic knowledge of JavaScript. The test subjects were given a brief introduction to the features of IDVE, had to solve a series of simple programming tasks with the environment, and answered a brief survey about their experience. Results indicate that more than half of the participants were able to use the features of IDVE effectively to solve the programming and verification tasks. All participants reported that they found the tools either helpful or potentially helpful. However, an improved user interface design might enable more programmers to successfully use these features. 6.2, environment integration. In order to be useful in practice, program verification has to be integrated into the development process. Ideally, feedback provided by the verifier should be instantaneous, continuous, informative, comprehensible, and actionable. Instantaneous feedback requires the verification procedure to be fast enough to avert noticeable delays. This also enables continuous feedback by implicitly invoking the verifier after each code change. Most program verifiers, including asVerify, can check small to medium source files in less than a second and thereby enable sufficiently fast feedback. Providing comprehensible and actionable feedback, in contrast, is still a major challenge for program verification because the complexity of the verification procedure can result in errors that are hard to understand. IDVE is an integrated development and verification environment that integrates an interactive verification inspector and a counterexample debugger to address this issue. The implementation of IDVE is open source and a live demo is available online. 6.2.1 Basic line markers. Each verification condition identified by the verifier corresponds to a location in the source code, such as a postcondition of a function definition, a function call that has to satisfy a precondition, or the arguments of a binary operator which have to adhere to a certain type. As a basic form of environment integration, the source location of a verification condition can be displayed as an annotation or line marker in the code editor. Figure 6.2 shows an example of an editor with line markers to indicate verification conditions using different icons for verified, unverified, and incorrect results. Here, a result is considered incorrect if the generated test causes an assertion violation, while an unverified result might have failed verification due to a missing loop invariant rather than an actual bug in the code. In addition to the icon, these line markers also include a short message that can be displayed by hovering the mouse over the icon. In addition to verification errors, this type of feedback is also common for type errors. Indeed, the line markers in IDVE are also used for other errors, such as parsing and scoping issues. While this integration is relatively simple, non-intrusive, and self-explanatory, the provided feedback is limited and may not be sufficiently detailed to help the programmer understand and fix potential verification issues. 6.2.2 Verification Condition Inspector. By selecting one of the line markers discussed in the previous section, an additional panel can be opened with an interactive inspector for verification conditions. Figure 6.3 shows an example with an active verification inspector. Here, the verification condition in line 4 cannot be verified and is selected in the editor on the left. The panel on the right then allows interactive inspection of the verification condition. In particular, the inspector lists assumptions such as preconditions and invariants. While there are no relevant assumptions in this example, the user can enter an assumption in the form of Boolean expressions and add it to the verification context for the selected verification condition. For example, by entering the JavaScript expression type of n equal number, the verification condition will be re-examined with the new assumption, causing the verification of res to be greater than or equal to 0 to succeed. Similarly, the inspector displays the assertion proposition, but also allows additional assertions to be entered by the user and tested for the same assumptions and context. This feature of the verification inspector can be useful for interactive exploration and experimentation with the verification context without having to change the original source code, analogous to how interactive debuggers supersede printf debugging. This feature is novel in verified programming environments, as existing environments, such as Daphne IDE, only display information about verification conditions without providing ways to interactively alter assumptions and assertions with the verification inspector. 6.2.3 Counterexample pop-ups. For each failed verification condition, a counterexample is synthesized based on the SMT solver output. This counterexample includes concrete JavaScript values for free variables, such as function arguments and mutable variables in the surrounding scope. IDVE displays these counterexample values for the currently selected verification condition as pop-ups in the editor. These pop-ups are directly connected to the relevant variable or parameter definition, but they are also obscure. The source code below, and they only display short summaries that may be inadequate for complex values such as nested objects and arrays. Visualizations of nested data structures is also an important challenge for regular debuggers and development tools. 6.2.4 Debugger integration. Even with information about values of free variables, such as those displayed with editor pop-ups, it may not be obvious why a post condition may not hold, especially for longer functions and methods. In these cases, it might be helpful to inspect the current values of variables at different points in the function body. In general, this can be achieved by using an interactive step-by-step debugger. In the context of a failed verification condition, a counterexample test can be automatically generated for the purpose of debugging. Running this test will either result in an assertion violation, which serves as a concrete witness for a bug in the code, or annotations, or a success test execution without error, which indicates that a false positive was caused by the conservative static analysis of loops and recursion. In both cases, stepping through the code can help with understanding the verification issue and locating the root cause of the bug. There are two possible approaches for debugging the counterexample test. On the one hand, the generated test could be exported and debugged with a traditional debugger in a separate tab or window. This would ensure a traditional debugging experience and could even enable the generated test to be added to an existing unit test suite. However, this approach requires the user to switch context between the original code and the test. Moreover, this approach exposes the automatically generated test code, which may not be human readable and whose mapping to the original source code may not be obvious. On the other hand, it is possible to hide the automatically generated test code and debug the counterexample directly on the level of the original source program. Essentially, the debugger internally steps through the generated test while highlighting expressions and statements in the original source code that correspond to the current code fragment in the test. This approach avoids context switches, but it might cause an unexpected order of execution steps in the visible source code if the control flow in the generated test differs from the control flow in the original program due to inserted dynamic checks or contract wrappers. Figure 6.3 shows an integration using the latter approach. Here the debugger is halted and the assertion res is greater than or equal to 0, and IDVE shows watched expressions, variables in scope, and the call stack. The user can add additional watch expressions and display their evaluation results. For example, entering res will show false as the returned value for this counterexample. Additionally, the execution can be stepped using standard debugger controls. In contrast to debugging regular executions, the integrated debugger of the verification environment includes both a dynamic context from the actual test execution as well as a static context representing the verifier state at different points in the code. For example, for ABS, the scope panel contains both the function value used by the test execution in black and a synthesized function value in brown below. Only a single value is displayed if the value from the dynamic and static contexts agree. While this information is not relevant in this example, comparing the dynamic and static value of a mutable variable after a loop may help to understand missing or incorrect loop invariants. Internally, the debugger is implemented as an interpreter that operates directly on the JavaScript AST of the test code. This incurs a high performance penalty over standard debuggers and techniques such as source-to-source compilation, but it provides greater flexibility for incorporating additional features. For example, the IDVE debugger maintains both a dynamic execution and a static verifier context, and it provides a better debugging experience for stepping through function wrappers. 6.3. Evaluation and user study. IDVE was evaluated with a user study with 18 participants. This section describes the relevant research questions, the design of the user study, its results, and potential threats to validity. 6.3.1 Research questions. In contrast to the program verifier itself, the design of the integrated development and verification environment is difficult to evaluate due to the subjective experience of programmers and the large solution space. This user study aims to provide insight into answering the following 3 research questions in order to inform future designs of such environments. RQ1. Can IDVE assist in the development process? Do programmers use features such as line markers, interactive manipulation of assumptions and assertions, counterexample editor pop-ups, and integrated debugging if these features are available for solving a given task? RQ2. Is the proposed user interface helpful and intuitive? Careful consideration is required for the design of user interfaces of development environments in order to balance the amount of information and interactive controls. Therefore, this user study should determine whether the proposed design is generally perceived as intuitive or is overwhelming and cumbersome. RQ3. How does programming proficiency and prior experience with program verification affect utility? The proposed environment should ideally be accessible and usable by both novices and experienced programmers. However, programming expertise and experience with program verification might be a prerequisite for effectively using the proposed features of the environment. 6.3.2 Methodology. IDVE is still an early prototype and not yet ready for productive software development. Therefore, the user study focuses on how proposed features can be used for smaller programming and verification tasks. Test subjects had no prior experience with IDVE itself, but indicated to have at least basic knowledge of JavaScript and might have used other program verifiers before. The user study was conducted entirely online. Subjects were recruited with an invitation sent to a public mailing list and remained anonymous. 18 adults entered the study and were presented with a brief introduction of IDVE, followed by a series of programming and verification tasks, and finally surveyed about their experience using the tool. Appendix B lists both the tutorial steps as well as instructions, provided code, and hints for the experiments. Additionally, an archived version of these tasks is available online at https://verify.org/user-study-archived. For the first step, a guided tutorial introduced the source code editor itself, a simple verification example similar to the one in figure 6.1, an interaction with the verification inspector as described in section 6.2.2, and an interaction involving stepping through a generated test with integrated debugger discussed in section 6.2.4. After the tutorial, participants solved 3 short tasks. 1. The first experiment involves an incorrect factorial function. that causes an infinite recursion for negative arguments. This task can either be solved by changing the precondition or by changing the implementation of the function. Participants could use the verification inspector and the integrated counterexample debugger, but editor pop-ups were disabled. 2. For the second experiment, a correct implementation of six-sided dice rolling function was given. However, the function was missing postconditions necessary for verification of the subsequent code. Editor pop-ups and the verification inspector were both disabled, so only basic line markers were available for this experiment. The third and final experiment involved a function for converting the number of minutes since midnight into a 24-hour digital clock format. The provided code included bugs in both the annotations as well as the implementation. Both the verification inspector and editor pop-ups were available, but the integrated debugger was disabled. All experiments could be skipped at any time and did not measure time or success. Instead, test subjects proceeded to the next experiment at their own discretion and filled out a survey form about their experience at the end. 6.3.3 Results. A full record of survey answers for all 18 participants, including written comments, can be found in Appendix C. These answers provided empirical evidence toward answering the research questions above. RQ1, can IDVE assist in the development process? According to the survey results shown in Table 6.1, the usage and the perceived benefits vary for the three main features of IDVE. While half of the participants made use of counterexample pop-ups, the verification inspector was only used by 39% of participants and the integrated debugger by 28%. In total, 15 participants reported using at least one of the tools. When features were used, they are generally seen as helpful or at least potentially helpful. This indicates that IDVE can effectively assist programmers. RQ2, is the proposed user interface helpful and intuitive? As shown in Table 6.1, the verification inspector, the counterexample editor, pop-ups, and the integrated debugger were considered helpful by 33/55/44% of the subjects. Another 50/39/44% reported that these features could be helpful with an improved user interface. Additionally, a third of the subjects tried the verification inspector and counterexample pop-ups, but reported being unsuccessful. Overall, the results suggest that the user interface is an important factor for using verification in practice. Incidentally, half of the participants did not try to use the integrated debugger despite considering it helpful or potentially helpful. This might be a result of the experimental setup with the programming tasks that were too trivial to require debugging, but it might also indicate that the debugger integration might benefit the most from user interface improvements. RQ3, how does programming proficiency and prior experience with program verification affect utility? As part of the user study, participants ranked their JavaScript proficiency on a scale from 1 to 5, novice and expert, and indicated whether they had prior experience with program verification. Table 6.2 shows how this related to usage and perceived benefits of IDVE. Here, it is most noteworthy that all participants, including those without JavaScript expertise or prior verification experience, found at least one of the features helpful. Also, no significant differences were reported on the actual usage of these features in the experiments. While these results suggest that IDVE is accessible for both beginner and experienced programmers, the number of test subjects may be too low to fully support these conclusions. In fact, 3 of the participants remarked in written feedback that a more comprehensive tutorial about program verification would have been helpful. 6.3.4 Threats to validity. The user study had a limited scope with only 3 short programming tasks and 18 participants. Therefore, it is possible that a broader user study with larger programming projects and more participants would yield different results. However, while scalability could be a concern for the runtime performance of the verifier, it can be expected that the responses of this user study regarding usability are at least indicative of a general trend that would be observed by a larger user study. Additionally, the results of this user study might be specific to JavaScript. It is possible that this approach for an integrated development and verification environment would be inadequate or impractical for a different programming language or a different domain. For example, the integrated debugger for automatically generated tests may not be applicable to programs involving concurrency or input-output to external services or components. 6.4. Future work and conclusions. Program verifiers enable expressing and checking various correctness properties, but understanding and debugging resulting verification errors can be difficult. To assist programmers, this chapter proposed an integrated development and verification environment and discussed its features. The environment enables inspection of verification conditions, including the option to interactively add or remove assumptions and assertions. Additionally, the environment provides executable counterexamples and step-by-step debugging for failed verification conditions based on automatically generated tests. To evaluate this approach, a user study with 18 participants was conducted. The proposed development and verification environment is generally seen as helpful, especially its feature for displaying counterexample values as editor pop-ups. However, the user study also found that interface design is an important factor that could be improved to ensure that the proposed environment integration is useful in practice. There are still open questions that could be addressed by future work, such as whether this approach scales to larger applications with multiple developers and how it could be applied to other domains and programming paradigms. In a way, ideas only count for a little in computing because you kind of have to implement the stuff. This is the part of the story that really makes me clutch at my throat, because every time you implement something, 5 years go away, and you do learn something. Alan Kay. Chapter 7, Related Work. This chapter outlines and briefly discusses relevant publications and important related research projects in the areas of live programming, program verification, automatic test generation, and integrated verification tools. 7.1. Live programming. The term live programming is used in different contexts and can denote the act of programming as part of a live art or music performance, but it can also refer to programming environments that continuously evaluate expressions and display the results alongside the code. In the context of this thesis, live programming is the ability to change the code of a running stateful application without restarting it, also known as hot swapping or dynamic software update, while providing immediate and continuous feedback about these code changes. Such live programming systems were described and motivated by Hancock and further explored by systems like Subtext, which uses a tree representation of constantly executing expressions, Superglue, which uses dynamic inheritance and functional reactive programming, and Elm, which demonstrates live programming and time traveling with first-order functional reactive programming. The solution described in Chapter 2 is based on earlier work that requires UI rendering and stateful computation to be separated, and that prohibits function values, closures, in the application state to allow the state and the code to be updated independently. A paper by Burkhardt et al. Described this idea for touch develop. More recent work outlined the possible design space between live programming systems that resume computation with a possibly inconsistent state, and systems that record and replay execution, as well as introducing managed time as a concept for supporting both live programming and time travel, and approaches that combine the language design with the design of the programming environment. The main contribution of live programming research for this thesis is the design of a simple programming model based on the model view update pattern and an environment integration for JavaScript that offers similar live programming capabilities as Elm and Touch develop, without requiring special syntax, type annotations, or library integration. Additionally, the proposed approach can also be easily extended to support back-in-time debugging and runtime version control, i.e. the ability to navigate to past execution states and passcode versions while providing continuous feedback. Programming by example allows users to create and modify programs by providing examples instead of editing the source code. Prior work on programming by example and programming by demonstration ranges from domain-specific macro systems, visual programming systems, and automatically inferred string processing rules to depth-limited generate and test approaches for general-purpose programming languages. Most notably, CodeHint synthesizes short Java code snippets at runtime based on user-provided queries. In order to synthesize larger code snippets, SMT solver-aided approaches may be a promising alternative. In the end, the use of SMT solvers for program synthesis is closely related to their use for program verification. Indeed, program synthesis can be seen as generalized program verification, where the output is not an error message or counterexample, but an inferred code candidate that repair the input program to satisfy the specification. Chapter 2 also presented an approach for live programming by direct manipulation. Direct manipulation of the graphical user interface is a well-known form of user interaction, with popular applications in Smalltalk, Morphic, and others. However, direct manipulation usually only affects the current state of visible objects. Recent work on pro-direct manipulation shows how direct manipulation of SVG vector graphics can be used to automatically modify the SVG rendering code. The same idea has also been applied to manipulation of string contents in PHP web applications. These two projects are most closely related, but in contrast to the approach in Chapter 2, they do not support live code updates of stateful applications without restarting the execution. 7.2. Program verification. There have been decades of prior work on software verification, in particular, static verification of general-purpose programming languages based on pre- and post-conditions has previously been explored in verifiers such as ESC/Java, Javert, Daphne, and Liquid Haskell. ESC Java proposed the idea of using undecidable but SMT solvable logic to provide more powerful static checking than traditional type systems. Their proposed extended static checking gave up on soundness to do so and instead focused on the utility of tools to find bugs. Javert is a more recent program verifier for JavaScript. It supports object-oriented programs, but in contrast to its verify, does not support higher-order functions. Other related work on static analysis of JavaScript programs include loop-sensitive analysis, the TAGS type analyzer for JavaScript, as well as type systems such as TypeScript, Flow, and dependent JavaScript. As verify follows as different approach as it relies on manually annotated assertions that are generally more expressive than types. Daphne seeks to provide a full verification language with support for both functional and imperative programming. Daphne offers programmers advanced constructs for verified programming, such as ghost functions and parameters, termination checking, quantifiers and user-supplied annotations, and reasoning about the heap. However, in contrast to its verify and Liquid Haskell, Daphne requires function calls in an assertion context to satisfy the precondition instead of treating these as uninterpreted calls. Therefore, Daphne does not support higher-order proof functions, such as those shown in section 3.4.4. Additionally, quantifier instantiation in Daphne is often implicit and based on heuristics, which often result in a brittle and unpredictable verification process. In trying to find a compromise with predictable checking, but also a larger scope than traditional type systems, Liquid Haskell is most closely related to its verify. In fact, the refinement type system discussed in section 4.8 loosely resembles its formalization by Vazou et al. More recently, Liquid Haskell introduced refinement reflection, which enables external proofs in a similar way as the spec construct in its verify, and proof by logical evaluation, which is a close cousin to the quantifier instantiation algorithm in section 4.3, but is not based on triggering matching patterns. In contrast to Liquid Haskell, as verify is not based on static type checking and thus also supports dynamically typed programming idioms such as dynamic type checks instead of injections. Finally, trigger-based quantifier instantiation, as used by the decision procedure described in section 4.3, has been studied by extensive prior work. The instantiation in his verify is specifically bounded in order to prevent matching loops. But further research could provide this kind of instantiation as a built-in feature of off-the-shelf SMT solvers. 7.3. Automatic test generation. While the goal of this thesis is focused more on programming environments, Chapter 5 described the automatic test generation of verification counterexamples as a basis for further environment integration. Counterexample generation is an essential concept for both SMT solving and theorem proving. Automatic test generation, i.e. generation of executable counterexamples, extends this idea and is a common technique for both program analysis and verification. For program analysis, techniques such as symbolic execution, white box testing, and parameterized testing use both path conditions to reason about control flow and generate random inputs in order to explore more program paths and thereby achieve higher test coverage. The approach in this thesis, however, is based on formal verification rather than symbolic execution. Here the main difference is the reasoning about loops and recursion. While verification requires manual annotations to avoid false positives, symbolic execution approximates the program behavior and may produce false negatives. On a side note, Chapter 3 targets JavaScript, a dynamically typed language, but automatic generation of error witnesses has also been explored for type errors in OCaml. Furthermore, Heidegger and Piemann previously presented a system for annotating JavaScript code with contracts that are used for guided random testing. However, instead of using a static analysis such as program verification, the contracts have to be labeled explicitly by the programmer to guide the random testing. Similarly, Klein, Flatt, and Findler proposed a system in which test inputs are generated for stateful programs by randomly creating primitive values and objects, calling random functions and methods available in the current context, and synthesizing function bodies. This approach is similar to the test generation presented in Chapter 5. However, provides better support for object-oriented programs, and it might not be able to explore deeper issues due to the black box generation of test inputs. Automatic test generation has also been previously explored in the context of program verification in systems such as Key, for techniques such as abstract interpretation, and for runtime verification. For partially verified code, Christakis, Mueller, and Wustholz proposed to use residual assumptions for complementary checking and dynamic testing in order to find more errors. Alternatively, conditional model checking is based on a condition that models control flow for properties that cannot be verified. This condition can either be translated back into a program that represents the unverified part, or alternatively, the unverified assertions can be used as slicing criterion for the original program. The residual program is then used for dynamic testing. While conceptually similar, the automatic test generation presented in this paper targets higher order functional programs and requires explicit invariance for loops. More recently, Nguyen and Van Horn presented an approach for generating counterexamples for higher order functional programs. The paper uses a restrictive core language similar to simply typed lambda calculus and finds counterexamples by SMT solving with an approximation relation for stateful programs. Finally, for partially verified programs, verified assertions and invariants that depend on unverified verification conditions are vulnerable. So robustness testing might be applicable in these cases. 7.4. Integrated verification tools. There has also been prior work on debugging tools in the context of program verification. Even without static analysis, annotations such as function contracts may benefit from tool support such as dynamic activation, deactivation, and dedicating debugging features. Timchuk, Kafari, and Nierstrats recently investigated the integration of static analysis in a development environment by conducting interviews and concluded that this integration is essential for adoption. For program analysis with symbolic execution, Henschel, Bubel, and Hanwol recently presented a symbolic execution debugger that is integrated into Eclipse and offers a similar user experience to traditional debuggers. In the context of program verification, work on dedicated debugging tools overlaps with research on interactive theorem provers. For example, the proof script debugger for the key system offers step-by-step debugging for proof scripts and inspection of the verifier state as assistance for theorem proving. The most closely related research in the context of integrated development and verification environments is the work on tools for Boogie, Daphne, and Viper. In particular, Leguz, Lino, and Moscal presented a verification debugger for Boogie, a low-level verification language used internally by verifiers such as Daphne. At the same time, Daphne programs can also be debugged with an integrated development environment called Daphne IDE that addresses feedback about verification issues similar to the environment presented in Chapter 6. Daphne IDE also allows inspection of counterexamples, including the state of variables at different stages in the verification of a function body. However, in contrast to the environment presented in Chapter 6, it does not enable the user to interactively modify assumptions and assertions of a verification condition. Computers are useless. They can only give you answers. Pablo Picasso. Chapter 8, Conclusions. Computer programming is the act of specifying the intended behavior of software. The translation of the mental model into executable program code is challenging. Moreover, discrepancies between intentions and actual program behavior can be difficult to understand and to fix. This is an inherent problem of programming that persists despite future advances in artificial intelligence. However, it is possible to assist programmers with programming environments and programming language features. For example, live programming enables a faster feedback cycle by allowing live code edits to running programs, and program verification lets programmers specify the expected behavior with logical propositions that will be checked against the executable code to automatically detect errors. Neither of these two techniques is new, but both are currently gaining renewed interest by both academic researchers and professional programmers. While these concepts are to some extent orthogonal, a live programming perspective could inform the design of a programming environment for verification with an emphasis on interactive experimentation and continuous feedback. This poses the following question: how can live programming environments support verification to provide a better programming experience? 8.1. Discussion of research method. In order to answer the question above, the research for this dissertation involved design proposals, implementations, formal developments, and empirical evaluations. More concretely, the research was primarily guided by prototype implementations that demonstrate how certain features would affect programming for smaller programming problems and example applications. Building simple programming environments from the ground up has both advantages and disadvantages over adopting and extending existing solutions. On the one hand, it enables quick experimentation in a large design space with minimal constraints about the language or the user interface. Also, small online live demos might reach a wider, non-academic audience and thereby illustrate the idea and feasibility without the need to install local software. On the other hand, the custom programming environments implemented for this thesis research have no existing users and are generally not mature enough for productive use on real-world projects. This makes usability aspects difficult to evaluate, especially with regards to scalability for larger programs, coordination within programming teams, and long-term benefits and costs for the software development process. In addition to prototype implementations, the proposed designs were also formally defined. These formal definitions describe the core idea in a minimal and concise way, and they enable proofs of properties independent of concrete specifics of existing systems or programming languages. However, these definitions may not perfectly model the actual system and are also relatively dense and hard to understand, especially for non-academic readers. The author of this dissertation also used this method for other topics in programming language research that is not included in this thesis, such as work on a lightweight static effect system for JavaScript based on SMT solving, a project involving declarative definitions of time-varying values and their dependencies with reactive variables, and a refactoring method for replacing code with macro invocations by running macro expansion in reverse. 8.2 Summary of Results. The live programming system presented in Chapter 2 is based on ideas from functional and reactive programming and ensures continuous feedback for live code updates and similar to prior work by Burkhardt et al. And others. However, the proposed system is based on event-based UI programming JavaScript and the model view update pattern to separate rendering from event handling. Thereby, the programming environment can support back-in-time debugging, runtime version control, and live programming by example. The latter enables live code edits based on direct manipulation of the output by the user. The work on program verification is partly inspired by existing program verifiers such as Daphne. However, heuristics and inference techniques in program verifiers can result in a brittle verification process without means to inspect and understand potential verification issues. Furthermore, Daphne requires type annotations in addition to preconditions and thereby introduces complex interactions between type checking and verification. Based on a novel approach for verification, the program verifier described in Chapter 3 enables verification of JavaScript programs, including higher-order functions, without traditional type annotations or typing rules. The underlying quantifier instantiation algorithm ensures that the verification process remains predictable and avoids timeouts. Finally, a formal development given in Chapter 4 proves that evaluation of verified programs adheres to the annotations. This program verifier forms the basis for an integrated development and verification environment described in Chapter 6. By integrating directly into the verification process, the environment can support features that may not be easy to implement for existing program verifiers or environments. While the original goal was to create a live programming environment for verification, live code updates are equivalent to regular code updates for the purpose of static verification, so live programming does not directly interact with program verification. Nevertheless, the design of the environment is informed by live programming in the sense that experimentation and immediate feedback are primary objectives for its integrated debugging features. In particular, the environment displays details about verification conditions similar to the Daphne verification debugger, and it also enables live updates to assumptions and assertions of verification conditions. Thereby, programmers do not have to add assert statements to the code, re-verify the program, and switch context away from the verification inspector to obtain feedback. Any failed verification condition can also be examined by the means of an executable counterexample that enables step-by-step debugging through an automatically generated test case. Finally, a user study with 18 participants with and without prior program verification experience found the majority of participants were able to effectively solve small programming and verification tasks with the environment. The environment was generally seen as helpful or potentially helpful, with the user interface design as an essential factor for utility. 8.3 Future work. The theoretic work on formalizing the program verifier and the lean theorem prover enables both a soundness theorem for verified programs as well as a comparison with refinement type systems. In particular, it is possible to define a translation from types to annotations, and both cursory paper proofs and experimental evidence suggest that any well-typed program translates into a verifiable program. However, a full formal proof of this conjecture in an automated theorem prover remains open for future work. The main difficulty encountered while working on this proof is the quantifier instantiation algorithm and the quantifier nesting bound. It is possible that an alternative algorithm without reference to the quantifier nesting bound would simplify a potential proof in a way that its result could be extended to the algorithm presented in this thesis. A second area for future research is an integrated approach for using examples alongside verification annotations as a basis for synthesis and program repair. It is noteworthy that both the live programming by example mechanism in section 2.4 and the test generation in section 5.4 synthesize program code for different purposes. Ideally, program verification could be extended such that the output is not just an error message or a counterexample, but a code candidate that repairs the program according to examples and specifications. Essentially, formal specifications can be used to restrict the search space for program synthesis, analogous to examples in programming by example systems. Particularly, GUI applications might benefit from such an approach, as concrete examples are better suited for specifying the intended look and behavior of the GUI, while verification annotations are more appropriate for documenting and specifying application logic. Therefore, an integrated approach for program synthesis and repair based on example and verification would combine both advantages. Finally, the program verifier and the programming environments developed as part of the dissertation research are lacking some functionality that would be essential for productive use, such as termination checking, module imports and exports, and a preamble with verification definitions for all global objects, methods, and functions in JavaScript. Continued work on these implementations would make it possible to evaluate the approach for developing larger applications. Similarly, a larger user study with teams of programmers might yield more insights about the potential benefits and limitations about live programming, program verification, and their integration in a programming environment. Participant 10, JavaScript experience 1/5, program verification experience, yes. Verification inspector. I entered the ones from the tutorial as suggested. Yes, but it also calls for more logical foundation in introductory classes. Counterexample pop-ups. I would have liked a cheat sheet for the parts that were not a tutorial. Maybe I'm a little tired and can't figure this out right now. Getting the answer like in the tutorial would give me something to chew on. The feature is helpful. Integrated debugger. Used this feature in experiments. The feature is helpful. Comments. What I want to know as a layperson is, will there be some AI autopilot who not only can tell me something is wrong, as this does, but pretty much gives me the right answer every time? That's what I want, a glorified spell checker.